presentation. So now I will talk about the symmetric polynomials in three non-commuting variables. And this is a joint work with Vesselin Drensky and Jörg Koppitz. And the grants that we have that supported our research, and we are thankful. So the basic notions are I just mentioned. K is a field with characteristic 0. Let's have a xd is the set of variables x1 to xd, and unusual polynomial algebra in D variables, and free associative algebra kxd. And the general linear group of degree D acts canonically from the left on the vector space with the set xd, and this action could be extended diagonally in a usual way. So what is interesting here is if G is a subgroup of the general linear group, to consider the algebra of G invariants under the action of this group, and this algebra actually consists of all polynomials who stays invariants under this action. And what is the problem now? How to describe this algebra of invariants? And first of all, I'll try briefly to pass through the algebra of invariants when the algebra is polynomial algebra, because there all the things are known. And after that, we'll try to change the algebra of the polynomial algebra with another non-commutative algebra, and try to compare what will happen and what will looks like the commutative case and what not. So first, let's back to the problem how to describe the algebra of invariants of polynomial algebra kxd, and is this algebra finitely generated for all subgroups G of the general linear group? And this problem is stated by Hilbert in the famous 14th problem of the Hilbert from the International Congress of Mathematicians in Paris, 19th century. So the answer is given by several scientists, mathematicians, if the group is finite. So many authors say that the answer is yes. If G is reductive, again yes, due to the work of Hilbert. In general case, the Nagata gave counter examples in the 1950s. And this is some history to mention the names of the people who worked and start working on invariant theory. And the second important problem is is algebra of invariance is finitely if this algebra is generated by f1 to fn, then it is a homomorphic image of polynomial algebra of n variables. So the problem actually is to find the generators of ideal of the kernel of this homomorphism. And the answer is to find the explicit sets of generators for different group G. From the Hilbert basis theorem, we know that every ideal of a polynomial algebra key Yn is finitely generated. And this proof, non-constructive proof, was accepted very skeptically from many of his contemporary mathematicians, even the famous comment of Jordan, das ist nicht mathematics, das ist theology. I believe this is a myth. So further going on, if G is a finite group, so the algebra of invariance is isomorphic to the algebra of polynomial algebra in G variables, if and only if G is a subgroup of general linear group is generated by pseudo reflections. And let's count how many are the invariants. So if the algebra of graded space, algebra invariance is a graded vector space, and all component is a vector space of the homogeneous polynomials of degree n. So we have the grading of algebra of invariance. And here is the Hilbert series, and the coefficient in front of the variable of the power n is just the dimension of the nth component of the grading. Some useful formula how to calculate the Hilbert-Poincare series when G is finite and infinite, and some other helpful results. But now let's try to change this beautiful commutative case and replace the polynomial algebra KXT with another non-commutative algebra. But we don't want to refuse of some of good properties of polynomial algebra. So the most natural candidate is the free associative algebra, or the algebra of the algebra of polynomials in D non-commuting variables. Okay, this choice is clear because this algebra has the same universal property as the polynomial. So yes, the universal property is clear. If we have a mapping XD to commutative algebra, so this can be extended in a unique way to a homomorphism from polynomial algebra. But the same for the free associative algebra. Now let's consider the symmetric polynomial in free associative algebra generated by the variables. So these are the polynomials of the symmetric ones, but the variables are non-commutative. So there is a very interesting paper and good results in this paper from Margaret Wolf appeared in 1936. And she described the symmetric polynomials in this free algebra. And what could be the next step? So to develop a non-commutative invariant theory and study the invariant algebra when we have for a free associative algebra under the action of some group G. And of course, one can go further if change or replace this algebra with another one. So could be Lie algebra, free non-associative, relatively free variety of algebras, etc. But I would like to mention some results of Margaret Wolf, which are really nice. And okay, the paper is written very nice, but somehow I'll translate in our language the results. So first of all, the symmetric polynomials in non-commutative case, the definition is the same, nothing different. So we have a symmetric polynomial if it stays invariant under the action of changing variables using the permutation of the symmetric group, and we use the standard notation. So the sum of f means that the sum runs through all the permutation of the symmetric group. And what else? Yes, the symmetric group SD acts on the set of monomials at D and split it in orbits. And if we choose the one monomial for each orbit, then the algebra of invariance has a basis consisting of all such symmetric polynomials, some U. And the main result of one of the main results of Wolf is this one. So the algebra of symmetric polynomials in D non-commuting variables is a free associative algebra, and it has a homogeneous system of free generators let's say J, such that for any n greater than 1, at least one generator, it has at least one generator of degree n. And the number of homogeneous polynomials of degree n is the same in every homogeneous free generating system. And every symmetric polynomial in D non-commuting variable is the presentation F is a sum of coefficient from the field and some product of the polynomial generating sets. And I'm not going to prove, but just to mention the important result. So if we have a monomial, but first order lexicographically the variables x1 to xt, and if we have a monomial, we're interested in leading ones, of course, leading monomial. So the first letter will be x1. This is pretty clear. And the other important observation, if we have monomial like this k plus 1 and after that another one, and the first k depends on the letters from 1 to p, that means that the next one, if it's different from 1 to p, that this variable x I k plus 1 will be exactly x p plus 1. So the index here will be exactly p plus 1. Okay, and this is for all leading monomials, some examples of, again, from the paper in Margaret Wolf. And okay, the leading monomial of product of two polynomials actually is the product of leading monomials of F1 and F2. This is the same as commutative case, and only one observation that if we have a leading monomial, so we can't have x1 in the end. So we have a monomial, but we can't have x1 in the end. And another forbidden thing for leading monomial is just we don't have a word x1, x2 in the middle. So we don't have such thing. Again, from this paper of Wolf, in the free generating set, in the free associative algebra in two non-commuting variables, there is precisely one element of degree n for each n. So this is from her paper, but let's now see what happens after this paper of Margaret Wolf. The first result after her paper in non-commutative case appears 30 years later. After that, lots of people work on this. And again, we're still interested in the algebra in invariants, G invariants. But the algebra here is a free associative, and this is the same as commutative case. And natural questions are: which results in commutative invariant theory hold also in the non-commutative case, and which results are not true? Okay, I'll mention here the theorem of Kalyukin, Dix, Forman, Harchenko. So it turns out that the analog of theorem of Hamilton for finite generalization for finite group in commutative case, in the non-commutative case, it's not the same actually, and it holds only in a very, very special case only. And for these special cases, okay, I'll say the theorem, let G is a finite subgroup of general linear group, and the algebra of invariant is finitely generative, and only G acts on the vector space with basis xd by scalar multiplication. But with Kalyukin in 1984 published a paper and suggested the additional action. Additional action here means that Okay, let's have a symmetric group Sn and acts from the right on the homogeneous elements of degree n in the free algebra by the rule. The rule is this one, and this actually means that we permute the positions. So if we have a permutation, what we're working in three variables, but we could have a monomial of degree n, and we take one permutation from Sn and just permute the position. And if the algebra, okay, we equip free algebra with this additional action, and if the characteristic of the field is 0 and G is a finite subgroup of general linear group, then the algebra of invariants with this additional action actually is finitely generated. Okay, this is the paper which we recite. And for example, here for this monomial x1 x2 x1, if we have the action 1 1 2, so this will change the position of the first and the second variable, not the variables, just the positions. And okay, another result from Lane and Kharchenko independently found that if G is a finite subgroup of a general linear group, and then the algebra of non-commutative G invariants is free. And here some machinery how to solve Hilbert series, and if we have I will mention this one only. If we have a set of variables, and this is the union of y1, y2, and the elements of yn actually are of degree n, and this indices grading on the free algebra ky, and the Hilbert series look like this one. So 1 over 1 minus g of z, where g is the generating function of the graded set y. Okay, this is helpful for our research. And now let's consider first the algebra of two the symmetric polynomials in two non-commuting variables, but equipped with another action, Kuryukhin action, that we can change the position. Of course, we can calculate the Hilbert series. It's easy to express the generating function of the generating set, which is actually z plus z squared and so on. So that means that the coefficients, all coefficients are ones. That means exactly the law of results that we have only one generator in the set of in generating sets. And but with if we have additional action from the right, this algebra is actually generated by the elementary symmetric polynomials E1 and T2. So we prove it, but I'm not going to go to details. And now for the case of three variables, we can solve, of course, the Hilbert series, the generating function of the free generator sets, and that's it. Actually, we found the generating function of the leading term of the free generators. So this looks like this one, and this section is really nice. Sometimes looks like a big mess, but actually it isn't. It's ordered somehow the things, and the main result here is that these symmetric polynomials in three non-commuting variables, but equipped with another Kuryukhin action, is finitely generated. Okay, this is known, but the generators again are the elementary symmetric polynomials U1, E2, E3. So I think that my time is over. I could continue a bit, but I'm not so sure that. Oh, 4.
So you have 4 more minutes.
Oh, okay. That's why I'll continue. I have some what to say. So if we have a symmetric polynomial f, and u is the leading term, so after this Kuryukhin action, it is actually equivalent to consider the polynomial with leading monomial v, but leading monomial v is somehow ordered. So first we put ones, after that x1s, after that x2s and x3, and we count the number of variables x1, and let they be a1, a2, a3 correspondingly. So these numbers in weakly decreasing. This is okay. This is more or less obvious, but it's a very nice property which we use to prove actually that every symmetric polynomials could be expressed in the elementary symmetric polynomial. So E1, E2, E3 are the sum x1 plus x2 plus x3, but because we are reading like a sum, they will appear 6 times because we have 6 permutation in S3, so we don't need these coefficients too. So E1, E2, E3, and another notation here is Pn is just sum of x1 of power n. And what we do in the proof is that first, consider several cases, and of course the leading monomials are what we're interested in. And the first one is to consider the leading monomial only with variable x1, so mean that we need to express Pn in terms of E1 to E3 from the elementary symmetric polynomials, and this is done by reduction. So the first 3 is more or less clear. The fourth one, we use Maple to find this recurrence relation. It's not that difficult, and once we get it, we prove it by hand because it's really okay. It's more or less natural. And if we have this for first 4 position, so it's easy just to put ones after the first 4 position, and if n is greater than k, this relation will be also true. And after that, consider the case when we have 2 variables. But these symmetric polynomials, which is sum and the leading monomial looks like this, could be expressed in terms of the polynomial p with the corresponding numbers. But we know already that they're generated by E1, E2, E3. And the third case, when we have 3 variables in all 3 variables in the leading monomial. So again this could be expressed in the p and symmetric polynomials in 2 variables, which already proved. So the theorem is done. Oh, actually, what I wanted to say that we believe, and our hope and hypothesis, and that this is true for we can generalize this, but this is on the progress, so we're working on it. So thank you.
So this is true for any number of variables then?
Sorry?
So the result is true for any number of variables?
Actually, we have a general theorem that says that this is true, that this is finitely generated with this additional action, but we don't know which are the generators exactly. But we believe that, okay, I believe that this is the E12, the elementary symmetric polynomials. But I haven't proved for in general case, I mean.
Yes, yes, yes. Okay, thank you.
I think there are no more questions, so let's thank you again. And we have a 4 minutes break. Continue. So I'm pleased to announce our second speaker today, Vincenzo Nardozza. The title of his talk is Differential Identities of UT3F.
Thank you very much. Good morning, everybody. To everybody, as I already said, but I repeat myself. And first of all, I thank the organizers for giving me the opportunity to present this talk. And before I talk about mathematics, I'd like to say something about Vesselin. Okay, the first time I read the name Drensky was in 1995, and in a paper of Vesselin about automorphisms or relatively free algebras. And later on, I read his book, Free Algebras and PI-algebras, and I found it ever inspiring, never trivial, and always interesting. And this is precisely the same feelings I have whenever I talk with Vesselin. I mean, this not is just about mathematics. It may be as well about history, about politics, about everyday life. Because Vesselin is not just an outstanding mathematician. He is a bright person, witty, positive, and deep. Antonio Gianbruno once claimed it doesn't matter whatever a bright person does, he will always shine. And this fits perfectly to Vesselin. I am sure all people gathered here share these same feelings. I wish you, Vesselin, a happy 70th anniversary, and the same for all next, or for all years to come, from the bottom of my heart. It was a pleasure to knowing you. And from my almost perfectly bad pronunciation, I try to say it in Bulgarian. Čestita 70. godišnjina Vesselin.
Okay, thank you very much. Especially for your photo, I found the same sweater from somewhere as in the picture.
Okay. So now stick to mathematics. This is what I'm planning to say. And first, I formulate the problem. So what's the problem? It's a very basic one in this formulation. Start with a field of characteristic 0. And the problem is to determine and describe the differential polynomial identities of the upper triangular matrices of size 3 under the action of its full Lie algebra of derivations. These two red words have to be precised. So, okay, nothing new. In strict analogy with the terminology, in the ordinary case, determine will mean final generating set, okay, not necessarily a basis, a minimal generating set, but a finite set of elements generating the set of the ideal of differential polynomial identities of this algebra. And describe means compute the differential codimension sequence, or possibly the differential co-character sequence of this algebra. Okay, why to study this problem? I take it from some distance. If you, in this situation, if you have a Hopf H, which is a Hopf algebra, acting on an algebra A, algebra means associative unitary F algebra. Okay, acting on an acting on A, one can define the HPI identity, HPI of the algebra A. This is not very, it is quite recent to propose to look things from this unitary point of view, in some sense. And the first remark about this was made by Berele in '96, then Turin and Linchenko, and until Gordienko and Kochetov in 2014. Because this notion encompasses ordinary identities, super identities, more general graded, G-graded identities, or to some extent, star identities, which are different kind of identities having this common ancestor. I don't know if the ancestor is a right word. Historically, is not is not right. But I wanted to avoid in saying these polynomials share a common root, because could be misleading. However, differential identities are part of the same family. But while the ordinary super graded with involution identities of relevant algebras, and with this I mean the full matrix algebras, the Grassmann algebras of an infinite dimensional vector space, or triangular matrix algebras and related algebras, in all these cases we have results of concrete of the investigation of concrete identities of these algebras. There are many gaps to which still wait to be filled. Okay, but we have several concrete identity known, but few is known about differential identities, even for basic ones. So far, for all I was able to find, just a few cases have been investigated, and these are the algebra UT2 of F, triangular matrices of order 2, under the action of the two-dimensional non-abelian or metabelian Lie algebra, I denoted by L2, or some of a one-dimensional subalgebra. This was in 1919, or the Grassmann algebra of an infinite dimensional vector space, when it is under the action of a finite dimensional abelian Lie algebra. And then myself and Onofrio Di Vincenzo studied the differential polynomial identities of a general triangular matrix algebra, but under the action of the same L2 as before, or some one-dimensional subalgebras of L2. And that's all. So I wondered, what about the polynomial identities, the differential polynomial identities of UTM of F under the full action, under the full derivation algebra? Okay, actually, this for m equal 2, this is precisely what Gianbruni and Rizzo did. But the problem is that this algebra is too small with respect to the general situation. The general situation was studied by in this paper with Di Vincenzo, but in this case is the Lie algebra acting on it, which is very small with respect to the general case. So in order to face this general description, I think that as a reasonable intermediate step, the differential polynomial identities of matrix triangular algebras of size 3 under the full derivation algebra is closer in showing the general situation and may give some clues, hints, or to understand, to be able to understanding the general situation. It is small, still small, but this is not a limit because it makes things easier to compute. Okay, so this is reason one. There is a maybe non-mathematical but strong motivation in these considerations to effectively face the problem. One has to mix a bit of Lie algebras, a good serving of PI theory, and we need a portion of representation theory of the symmetric groups. But most of all, they must be hot spiced by concrete combinatorial arguments. So it was funny. This was the second motivation. I think it is a strong motivation when you do something which is fun for you. It's not mathematical, but it's a very, very strong motivation for me. So let's say a quick overview on what has to come. In general, if F is a base field and A is an associative unitary F algebra, L is a given Lie algebra, we may consider the set of derivations of A, which I mean just F linear derivations, which that is elements of linear transformations of A, satisfying the Leibniz, well-known Leibniz rule. This form a set, we denote it by their A, and the Lie algebra L acts on A by derivation. For short, is an L algebra if it has been assigned a Lie homomorphism. Okay, and, by the properties of the universal enveloping algebra of L, this turns A into a right module of the universal enveloping algebra of L. Right module because I will stick to making letting the derivation act on the right. Okay. Then one selects, the structure is prescribed, one selects the homomorphisms about such structures, for short L homomorphisms, meaning all the algebra homomorphisms commuting with the L action, prescribed L action. Okay. One has to bring up a free object in the class of L algebras. This is done quite neatly. First one assign a countable set of non-commuting free indeterminates, and consider this algebra f of xl as the tensor algebra of this vector space. This is naturally an L algebra. And moreover, it is free on the set X in the class of L algebras, which means, as usual, that that any set theoretic map from X to any L algebra A uniquely extends to an L homomorphism. Okay, valuations essentially. Okay, this is the pure definition of this free object. Pure because it does not depends on other objects, but just on the given L assigned. In order to do computation, however, we have to make things a bit dirtier. We have to introduce some soil to to this purity. And this, by this I mean, in order to make computation, we have to represent concretely the object of the given prescribed Lie algebra L. So we have to fix a basis in L. I call this basis L with a prescribed order, linear order, totally ordered base. And then among the consequences of the Poincaré-Birkhoff-Witt theorem, this provides a basis for the universal enveloping algebra, canonical basis on the semi-standard words on the alphabet L. Then one may simplify the notation, and instead of denoting the simple tensors x tensor u for all indeterminate x and all vector bases of u, one simply write a formal indeterminate, formal letter, differential letter, x to the u. In this way, one may identify the original, the parent indeterminate x with the x under the unity, the unit of the enveloping the universal enveloping algebra, and call them ordinary letters. The set of the letters, differential letters, built this way, generates a free associative algebra, which is isomorphic to the original, the pure version. This is a free associative algebra, but as a L algebra, this is free just on X. And notice, one may notice that after this identification, the free associative algebra generated by X is a subalgebra of this new alpha associative algebra. The notion of differential polynomial identities then turns straight on, because since we have written these elements, the elements of this algebra as polynomial in differential identities, it is perfectly natural to say that a polynomial in this polynomial algebra is a differential polynomial identity of A, written this way for sure, if it vanishes under all L and L homomorphisms from the free algebra to A, or using the universal property, if F vanishes under any substitutions of elements of indeterminates of X by elements in A. The set of all these polynomials is a TL ideal, which is invariant, which means invariant under all L endomorphisms of the free algebra F of XL. And the generating set, okay, of a T ideal is the ideal generated, the TL ideal generated by a set of polynomials is the least T ideal containing that set. So the notion of what has to be meant by saying that a set of polynomials generates the ideal of A, or differential identities of A, is precisely this one. The T ideal, TL ideal generated by G coincides, is equal to the differential polynomial, the ideal of differential polynomial identities of A. Okay, this is almost the same as in the ordinary case, but differential PI theory extends PI theory, encompasses PI theory, and the identities of ordinary identities of A are genuine subset of the differential identities. Unlike other situations, for instance, for graded identities. But as a matter of fact, in order to describe these differential identities, one cannot forget the ordinary ones. One has to describe the ordinary ones as well. And this is a neat distinction between differential identities and other kind of H of algebra identities. Although being offspring of the same ancestor, but the differential polynomial identities tend to increase in complexity when one has to describe them with respect to ordinary identities, while generally for the other ones, there is an inverse trend. They tend to be easier, less complex in describing this in the description. Okay, now from now on, let A be UT3, L this one, and any derivation of the upper triangular matrices is inner, which means that it's an adjoint. Be realized as an adjoint. So this also for UT3 as well. This is a real more state. The theorem of Coelho and Porcino-Milius is in really much general. This is a part of the theorem. And we have an algebra, its derivation algebra, and we have to fix this to describe. This simplifies our task because one has to choose the suitable elements inducing the derivations. I made this choose. I depicted them in red and blue and black dots, meaning that the red dots are the derivation induced by these unit matrices. The blue dots by this one. The difference red and blue is just because here to keep the element on the right, I have to add a minus sign here. And delta is okay, as it is written. This is the best choice to work with. The structure of the Lie algebra is then clearly described by this the only non-zero Lie products among these elements. Okay, and we have to do another choice, the order among them. I made some experiment, and these settings with this order, these derivations, this basis is the most proficient in order to make computation. Maybe not the only one, but it worked. So we have a basis of automatically a basis of U of L, and it is generated by these words. But almost all of them are trivial variables, trivial trivial action. The action of the kernel of the action of the enveloping algebras on A is a T-ideal generated by these elements. So almost any basis elements vanishes. Just standard words of length less or equal to 2. Precisely these elements are still have non-trivial action on A. And this is a basis of the factor algebra. So we have just to take care of this, of the differential variables arising from these elements. And so we have the 47 generators of the idea. They are, okay, as you see, starting from these generators of the kernel of the action, we have a part of the identities which arise from their data generators. Okay. Then I marked in blue this one because this is a new identity, and this identity, together with the structural ones, I call them structural ones, kill almost any monomial in f of x or fx of L, because among the 81 monomial of length 2 available, this one kills the 76 other one together with these identities. Just 4 of them are survive. Then we have, so this is a strong identity. Then we have several other identities involving commutators. It is not reasonable to expect that one has to recall to memorize them, but at last we get also, we have to include this, which is the ordinary generator, the generator of the ordinary polynomial identities of UT3, together with some variation. There are 74. They are 74. I don't know if this is really a basis, a minimal set of generators, or if it is, it will be not easy to prove it, I think, I imagine. By the way, the idea of proving this equality, that they are really generators, is in two steps. A first reduction to multilinear polynomials, which is the same kind of arguments used in the ordinary case. And a second reduction is provided by passing to proper multilinear polynomials. And Vesselin taught me 100 or 200 things about this notion, and his use.
Vincenzo,
Vincenzo,
yes. I'm afraid that your time is has expired, so you should reach a quick conclusion.
Okay. So I thank you very much for the opportunity of talking, and thank you. And okay, just this long. Thank you very much. Sorry.
Thank you very much. Are there any questions or comments?
Have you thought about using the triple L algorithm to reduce the set of generators?
Can you repeat the question, please?
To reduce the number of generators?
Yeah.
Have you thought about using the triple L algorithm, the lattice reduction?
No. Just no. I did not use that algorithm. These generators. Okay.
Mm-hmm.
They are 47. Just counting.
Okay. Perhaps it could work. Perhaps. I don't know. Thank you.
Thank you. Okay.
If there are no more questions, then let's thank the speaker again.
So, good morning, everyone. It is really a pleasure for me to be here today. Sofia reminds me of good memories. Something like 5 years ago, I gave my first talk at the Department of Mathematics. I was a young, scared PhD student. And of course, during the presentation, Professor Drensky asked me questions. But I survived, and it is really a pleasure to be here. I want to thank also the organizers of the conference, particularly my dear Plamen, for this nice conference and also for the opportunity to give this talk today. And last but not the least, of course, let me say many wishes to Professor Drensky for his anniversary. And also let me thank him for incredible contributions to mathematics, to our theories and everything. It is really, really a pleasure to be part of this world in which you are. So thank you, Professor. You are very inspiring. Okay, and now I will go to mathematics. As the title, I will talk about some results of the theory of polynomial identities in the setting of superalgebras with pseudo-involution. And okay, a lot of people already define polynomial identities, the codimension sequence and other stuff, but just to fix the notation, I would like to repeat these notions. So we consider a fixed field F and an associative algebra A. Now, if we consider a countable set of variables, x1 and x2 and so on, the free algebra, f of x, is the set of all polynomials in these variables and with coefficients in the field f. Now, the definition of polynomial identities, we take a polynomial of the free algebra, fx1, xn, and we say that this is an identity for the algebra A when it vanishes under all substitutions in the elements of the algebra. This means that fa1, an is always equal to 0 for any choices of these elements. And clearly, the 0 polynomial is a polynomial identity for any algebra. For this reason, we talk about PI-algebras when they satisfy at least one non-trivial identity. And some easy examples. If we take an nilpotent algebra A with M with a nilpotency index, then we have that the product of m variables, x1, xm, is clearly a non-trivial identity for this algebra. And the same for any commutative algebra. It is a PI algebra since the commutator, x1, x2 minus x2, xn, is a non-trivial identity. Now, given an algebra, we can consider the set of all the identities it satisfies. And we denote such a set with the symbol I of A. This is an ideal of the free algebra. More is a T-ideal. This means that it is invariant under endomorphisms of the free algebra. And with these big words, we just mean that if we have an identity, for example, in two variables, we can put instead of variables polynomials, and we still get an identity. And another important feature of T-ideals is that every T-ideal is of this form. This means that given any T-ideal I, there exists for sure an adequate PI algebra A, such that its set of polynomial identities is the T-ideal we started with. So this theorem of Cameron 1987 represents a very important result in the theory, because it proved that in characteristic 0, every T-ideal is finitely generated as a T-ideal. So if we take any algebra, we maybe do not know all the identities, but we are sure that all of them follows by a finite number of special ones, the generators. Okay, I just want to say that this theorem of Cameron solved a long-standing conjecture of spect but in a non-constructive way. So it is an hard problem to find the generators of a T-ideal. Okay, from now on, we fix the field F to be of characteristic 0. And as I said, it is difficult to find the identities in general. And one of the reasons for which Regev in 1972 introduced the codimension sequence of an algebra. A lot of people already defined this object, but let me recall again that here, Pn is the vector space of multilinear polynomials. And we can consider just multilinear identities because in characteristic 0, every identity followed by a system of multilinear ones. Okay, in the same paper, Regev proved one of the most important features of this sequence, a sequence that measures in some sense the growth of the polynomial identities. So he proved that provided that the algebra is PI, so it satisfies a non-trivial identity, such a sequence is exponentially bounded. And in the same decade, Kemmer characterized those algebras having a polynomial growth of the codimension sequence. Finally, in order to conclude this part, I want to cite this celebrated theorem of Gianbruno and Zaitsev, 1999, in which they gave a positive answer to a mixture conjecture for associative algebras. They proved that the limit of the nth root of the codimension sequence always exists, and it is a non-negative integer. Okay. Now I want to start presenting some notions concerning algebras with additional structure. I will start just giving the definition of superalgebras first. So a superalgebra is an algebra graded by the cyclic group of order 2, Z2. And this means that A can be decomposed in the direct sum of A0 and A1 to subspaces called the homogeneous components of A, or the components of even elements and odd elements. They satisfy this property, and it is just this fact. If you multiply two elements of homogeneous degree 0 or two elements of homogeneous degree 1, we get an element in A0. Instead, if we multiply an element of homogeneous degree 0 and an element of homogeneous degree 1, we get an odd element, an element of A1. And an example, of course, matrices, 2 times 2 matrices can be seen as a superalgebra with this grading. Now, why these algebras, these superalgebras are important in the theory of polynomial identity? The slogan is, they allow reduction to the finite dimensional case. What I mean? What I mean? Kemmer meant this with his important theorem of 1988. He proved the following. So if we take any algebra A, we are sure that, thanks to Kemmer, there exists a finite dimensional superalgebra B such that the TL ideal of identities of A is the same of the TL ideal of identities of the Grassmann envelope of B. I didn't define the Grassmann envelope, but here the important thing is that instead of studying an algebra A that can be of infinite dimension, we just can focus on a superalgebra of finite dimension and study it instead of A. So this is one of the reasons these kind of algebras are important in the theory. Okay, and finally we can start talking about the main object of this talk, which are superalgebras with pseudo-involution. And we already know what a superalgebra is. And from this moment, our field F, that already was of characteristic 0, is also algebraically closed. Okay, a pseudo-involution on a superalgebra A is just a linear map from A to A, satisfying the following 3 properties. The first one says that the linear map is graded. So if we start with an element of homogeneous degree 0, 1, and we put the pseudo-involution, we get an element of the same homogeneous element, homogeneous degree. Sorry. The second property says that A star star can be equal to A in case our element A is of homogeneous degree 0. Instead, is equal to minus A when the element A is an odd element, an element of A1. And finally, the third property is very similar to that one of an involution, but we have that AB star is equal to B star A star always, except when A and B are both elements of homogeneous degree 1, so both elements of A1. I just want to remark the situation of the decomposition of the homogeneous component A0 and A1 when we apply the pseudo-involution. For A0, we have an unusual decomposition like in the case of involution, so in symmetric and skew elements. But when we consider A1, the situation is not the same, because according to property 2, we cannot have symmetric and skew elements of homogeneous degree 1, but instead we have the so-called I-symmetric and I-skew elements, where I is an element of our field satisfying the following property: I square is equal to -1. Okay. So an example, if we consider the 2 times 2 matrices, and this algebra I already presented it when we talked about superalgebras, and on this superalgebra, it is possible to define the following pseudo-involutions. They are the only two up to isomorphism actually, and they are called pseudo-transposed, defined this way, and pseudo-symplectic in this way. And the existence of pseudo-involution on finite dimensional central simple superalgebras was proved by Jaber in 2008. And 2 years later, Martinez and Zelmanov make use of pseudo-involutions in their paper in which they classified irreducible bimodals over finite dimensional simple Jordan superalgebras. Okay, now I just want to present some results of PI theory for this setting of algebras. And from now on, we fix A to be a superalgebra with pseudo-involution, and we write CNP of A to denote its sequence of pseudo codimensions. So I just introduced the sequence in the ordinary case, but with the same philosophy, we can define the pseudo codimension sequence, and so we can study also this object. In a paper with Martino, 2018, we first gave the analogous of Rege's theorem. So we proved that if a superalgebra with pseudo-involution A satisfies a non-trivial polynomial identity, then the pseudo-codimension sequence is exponentially bounded. And in the same paper, we also characterized those algebras with pseudo-involution having a polynomial growth of the pseudo-codimension sequence. This is the analogous of Kemmer's theorem. And finally, for this slide, I gave a positive answer for the Amitzer's conjecture for this kind of algebras. Actually, here we have to just restrict our research, our study to finitely generated superalgebra with pseudo-involution, but the result is the same. I mean, we proved that the limit of the nth root of the pseudo-codimension sequence always exists and is a non-negative integer. Okay, in more results in this paper with Martino, just accepted for publication, we studied other features for this kind of algebras. We proved that the codimension sequence CNP of A is eventually non-decreasing in the finitely generated case. And also we studied some results concerning the multiplicities of the pseudo co-character, in particular when the multiples are bounded by a constant or when it is bounded by 1. And also we studied algebras having pseudo colengths bounded by 3. The last result is that there is a link between the property of having the pseudo-colength sequence bounded by a constant and the fact that the pseudo-codimension sequence grows at most polynomially. Okay, and I want to conclude this talk with some work in progress. So again, A is a superalgebra, and we know what an involution is, but we say that an involution on a superalgebra is graded if it preserves the grading of the superalgebra. I already gave this definition for pseudo-involutions. And in another paper with Martino in 2018, we found the relations between graded involutions and super-involutions on the algebra UTN of n times n upper triangular matrices. But in general, you can do something similar to this for any superalgebra in which the odd part, so A1 is nilpotent. And the idea here is to find similar relations between pseudo-involutions and graded involutions. But I'm very confident that we can do this in general for any superalgebra, not just for superalgebra in which the odd part A1 is nilpot. Okay, and this is all, and I want to thank you for your attention.
Thank you very much for your talk. Are there any questions or comments? So, do you know where the notion of pseudo-involutions appeared first in the literature?
Where?
Where and for what reason?
Good questions. I think that this superstructure always appeared first in physics, something like superstring theory. I am almost sure for super involutions. For pseudo, actually, no, I'm not sure, but I'm sure that I'm confident that this can be related with physics.
Thank you. There seem to be no more questions, so let's thank Antonio again. And to continue with the next talk, so I'm pleased to announce our speaker, Jörg Koppitz, and the title of his talk is Presentations of Semigroups of Order-Preserving Partial Injections in a Finite Set. So please go ahead.
Thank you very much. At first, I want to say thank you for the possibility that I can take part on this conference. And I have to say some things that I like very much to take this conference because Vesselin Drensky helped me very much into the way here to be a member of the Bulgarian Academy of Sciences. My history, the connection with the Bulgarian Academy of Sciences starts in the end of the last century. I was Humboldt Fellowship initiated by Todorov, which unfortunately died a few months ago. And so I have a long relationship to the Bulgarian Academy of Sciences and also to the University in Blagoevgrad, and this relationships topped with the fact that I could member of the Bulgarian Academy of Sciences since 2017, and Vesselin Drensky has a large part on this to help me on this way, on this position. Thank you very much for him. And now I want to come to the subject of the talk. I have to say this: the subject is not 100% related to the topic of the conference, but I think similar things will be also done in ring theory. What is the idea of presentations? Presentations means you have generators. That means a base, and you have relations which describe the semigroup. And this work is together with a researcher from Thailand. Name is written there. This is Panzara Zaretto, and such work needs a little bit time, and in Corona time I had not so much contacts with other people, so I decided to make such a research which needs a little bit more intensive work. So, okay, let's go to the
Application.
Let's X be a set, and X star is the free monoid on the set X. This is nothing else than the set of all words that you can make with the letters in X. And then we consider a relation on these words. And by R sharp, we mean the congruence on X star, which is generated by R. That means we make it first the reflexive part, the symmetric part, then the compatible with the operation. It means the concatenation of words. And then finally, we make the transitive closure, which is an inductive process. So, okay. Now, what is a presentation? A presentation is, as already mentioned, nothing else as a pair, consisting of a set of variables and a relation over the books with this relation, with these variables. So, and we say that is a presentation if we make the restriction from the free monoid to this congruence relations, and we have a semigroup, and if this is isomorphic to the given monoid, then we have found the presentation. That means at first we must found the set X. What is the set X? The set X is nothing else as the generators of the semigroups. It must not be a minimal set. This is not required. And a set of generators. And R is the set of relations. It means we can find for the same semigroup different presentations, but the question is to find a good presentation. What is a good presentation? A good presentation is if the numbers of variables is low and also the numbers of relations not so high. So that means we every time ask how many elements in X and how many elements in R, and by a lower number we have a good presentation. So what we have to do more, we can say that is a presentation via an epimorphismus phi. So we know that M is isomorphic to the vector structure X star to the R sharp. So that means we can have to find the epimorphism from the free monoid in the monoid that we want to present, and the kernel is exactly the congruence relation. Of course, the kernel is a congruence relation that is known, but it must be exactly this congruence relations that is given by the relation R. So, okay. Now our first attempt was to restrict us to a positive integer. This is at the first attempt. This is quite useful, but it is not necessary to do this. So that means we have to set elements 1 up to n, and Tn is the full transformation semigroups, also called symmetric group. And I want to mention here that why we consider such transformation as semigroups, namely, it is known that each group is isomorphic to a symmetric group for a given set N, or it is infinite over any given set X. So, and a similar Kelly theorem or Kelly theorem for semigroups, we have the following, that each semigroup is isomorphic to a transformation semigroup. Transformations is nothing else as self-swapping from X to itself, but not more bijective. If you have a group, the bijections are bijective. Now we not more require the bijectivity. So, and it means if we have knowledge about the transformation semigroups, so we have the knowledge about all semigroups. So, and this is the set of all transformation. Tn is the set of all transformation from set 1 to n in the set 1 to n. So, and a pioneer of the research of transformation semigroups is Anna Eisenstadt from Russia, a Russian mathematician, and long time ago she initiated the research of transformation semigroup, and she found the presentation for the full transformation semigroup. Little bit. So, and now we can do the following. Now we can consider this n as a chain, and required that the transformation have a particular property, namely that you preserve the chain. That means if the two elements in relation, then also the image of these both elements have to be in this relation. And this property is called order preserving, and the set of all order preserving transformation forms a subsemigroup of the full transformation. What is operation? Operation is nothing else as the usual composition of function, also namely of transformation. So this is operation in the semigroup, and also Anna Eisenstadt found presentations for this semigroup of order preserving transformations. And as I mentioned already, it is interesting how many generators she needs to act for if you have a transformation on an element set, and then you look for all mappings from this set in itself, then you need exactly 2n minus 2 generators. This is like a base, and n square relations to find to describe the complete semigroup. Okay, so now we are interested in another order which is close to object from the graph theory. From the graph theory is known a path. That means you have errors from 1 to 2 to 2 to 3 and so on. And if you do the following, in each second step, you reverse the error. Here. So, and then you get a new construction, which is not called path, it calls fence. So, and you can see here, 1 is related to 2 and 2 is related to 3. And I have to mention only this what you see is related. There's no transitivity, nothing else. Like in the past, you have also not transitivity if you consider the graph as a ordered set, as a set with a relation. Then you have only the naviers 1 and 2, 2 and 3 are related. And now you see here in the fence, in each second position, we reverse the error. So, and then we get fence, and now we consider all transformation which preserve the fence. That means if two elements in relation, then the image elements also in the relation. And this set of all these transformations forms a subsemigroup of the full transformation semigroups or of the symmetric semigroup. So, and this is first done by
Rutkowski and Curry, but I'm not sure. I heard also somebody else before I've done this, but I'm not so really sure. That's why I'm not, if the real name of them, they done this before them or not. But this are, and what they have done, they have count the numbers of the elements in the set Fn. So that was, and they used different techniques and to find this, but the number of the elements is not so easy to describe. That's why I want to not give this number directly. So, what is a partial transformation? What is in a full transformation? We have as the domain of the transformation is the set 1 to n. If the domain is have not more to be the full set, then we speak about a partial transformation. So then we have the set of all partial transformations which preserve the fence. This is all also monoid. Okay. So and so in this semigroup was we considered already this semigroup, namely by Dimitrov, a mathematician from the Blagoev grad. We found the ranks of this. What means the ranks? It means the number of the smallest of the generating system with the smallest size. It means like a minima base or such one. We are found this for the semigroup, and later I go with other researcher from Thailand. We go over to the infinite case. It means we have not more a finite fence, or we have an infinite fence, and then the situation is completely different. If you go over from finite to countable, already to countable, all things are changed, and we are looking for and found some regular subsemigroups, namely countable infinite set of regular subsemigroups. And more, we studied the concurrences, and we found not all, but we claimed to found that we found all, but we could not yet prove that we found all concurrences on the semigroup of fence-preserving transformations on the natural numbers in the infinite case, and this both works was PhD thesis of Lohapan in Thailand. She worked 1 year together with me, and we found some quite interesting results concerning the semigroup. So, and now we consider the second order, namely this fence order is also a partial order. Another partial order is the linear order. So now if the symbols, I mean the linear order of the natural numbers, and we consider all order preserving partial transformations. It means now we mean really the order, not the fence order. We mean here the real order 1 is smaller than 2, smaller than 3, and so on. And also this is preserved. So, and then we consider this forms also a semigroup. And now we consider all partial injections. That means one-to-one mappings, but the domain must not be the full set 1. That means it's not only the permutations. And I have to say we have only two permutations which are fence preserving, and which but now we have this partial injections. So this is also subsemigroup, and now we consider a third subsemigroup, namely preserving the parity. That means the even number is mapped to an even number, and an odd number is mapped to an odd number. It is quite easy to see. This set forms also a subsemigroup of the semigroup of all partial transformations. Okay, and this is a set of the. Okay, now we make the intersection of all these semigroups, and say also additional that the inverse of them is also a partial phase-preserving transformation. So I want to give some examples of them. This means we have here. This is belongs to this semigroup. This belongs not, because you see this is not fence preserving. You can see 3 and 4 are related, but 3 and 6, the image, is not related. So other example which is not, this is not order preserving, because you have here in the image 3, 4, and then 1. Order preserving means this must be the numbers must be go down. And the other example is which is not belongs to the semigroup is this one, because this should not preserve the parity, and because you see 5 goes to 6, it means an odd number goes to an even number. So what is the aim of our research was to find a presentation for this semigroup. We started with some other semigroups, and maybe if somebody works already with presentation in other structures, know that it's sometimes not so easy to find the generators and the relations, and we restrict us to do this and found some results for this one. Now this is now a little bit technical. Now I want to find the generators. You see here a partial transformation where is a bang, then this maps, this is not to the, belongs not to the domain. That means the I plus 1, I plus 2, and I plus 3 not to belongs to the domain. The rest is the is of this form. So maybe then this is the inverse transformation of them. And then you have here partial injections. That means only all goes is the our fixed point, only I belongs not to the domain, and then we find a set of transformations which generates our semigroup. So that is a set of generators. We not claim that this is minimal, but this is a set of generators, and this is our theorem that we can prove. And now we need what we need for a presentation. We need for a presentation a set of variables, and usually we take this -1 or that's minus equal. Yes. So that means we need variables. We exactly take the variables, the generators, but we must resign it. That means we must give them other names. That's why I have to write by the generators every time bar, and by the variables I skip the bar. So then we have 5, 6, and -6 generators. What about the relations? We have a set of relations, and I want to give only examples. For examples that are these are idempotent. In this way, we can write in such a form. Then this is like commutativity, but not really. If you move the j after ui, you have to little bit change the index of this variable, and this ui is for several j's right 0, and in this case
left 0, and I want to not say all and several other relations. I want to only give some looks quite interesting, and now we denote by R all the relations that we have. That means R1 up to R5 and the rest. So what is the rest? So, and we want to show that our X, what I given in the first line, together with this set of relations, which is of course finite, is a presentation of for this one. So, and now what we have to do, at first we make the congruence relation by this one, and then we defined phi from the boards into our semi-group, our monoid, by the quite canonical operation that we maps each variable to a corresponding transformation. That's why it makes sense to, so, and in this way is, if you do this for the generators, then clear, then the epimorphism is defined for the complete semi-group, and now our claim is to show that this relation is exactly the kernel of this epimorphism. So how we do this? There are some techniques from the literature. At first, we have to show that all relations are satisfied by the semigroup. That is the meaning of this first subset. And how we can do this? This can be done by diagram. So we because it's finite, we write the diagrams of the transformations. We write the picture which maps maps of the right side of the relation and then of the right side, and then we see that is in both sides okay. And this can be by examples, and then we can think the rest is also okay. And so we have done this exactly for all. We have done this. Check it. This is working. So now the more work will make this direction, and the trick is that we define a set of normal words. So and we show that each word is related to such a normal word. By the given relations. This is the crucial point. And the second crucial point is that this mapping restricted to the set of normal words is injective, and to show this injective, and we have this one, then we can find very fast this. So I want to summarize what we have. We have 3 points, which gives us the which are enough to show that we this is a presentation. So this is how the 3 facts what we have. At first, this is a generating set. Then we know that the kernel is exactly to the congruence relation, which is generated by R, and the fourth fact is that this is the restriction of our function to the normal ones is injective, and by very important result by Ruskuch, which is a pioneer for find this partitions in transformation semigroups. We know that we have that our set is a.
Excuse me, Jörg, your time is expired, so you should reach a conclusion very quickly.
This was also my last slide, and I want to say thank you very much.
The last talk in this morning session is by Konstantin Delchev, and the title is Biangular Lines with Maximal Sum of the Squared Inner Products. So please give your presentation.
Thank you. First of all, I would like to extend my congratulations for the 17th anniversary of Professor Drensky, and to say that I'm very glad to be able to present a talk at the conferences dedicated to his anniversary. Now, I must say that while coding theory has some common points with ring theory and so on, this talk will live, so to say, in Euclidean spaces, and it will concern mostly, it will mostly concern the unit sphere in Euclidean space with the usual distance and the usual inner product that we see here. And when we are on the unit sphere, those two are trivially connected in this way, so we can always default to using the inner product because we want everything to be as linear as possible, not deal with any square roots or anything. And on the linear unit sphere in Euclidean space, we're interested with two main entities. First, it's spherical codes, and as with anything in coding theory, we call spherical code a finite subset of the unit sphere. And if its cardinality equals m and the maximal inner product, which is the same as the minimal distance between distinct elements, is S, then C is an NMS code. And the classic coding theory problems state that given certain bounds on two of these parameters, what's the best value for the third one? Biangular lines, our second entity of interest, is trivially connected to it. We call a set of lines passing through the origin of the n-dimensional Euclidean space biangular lines if they admit exactly two angles between them. And if we intersect this with the unit sphere, we obtain a spherical code, which spherical code is antipodal. If it contains one point, it contains the exact opposite. And now it's an antipodal spherical code with 5 inner products, plus minus S1, plus minus S2, and 1. And such spherical codes with antipodal properties with small distances, a number of distances, they're very useful because they're frequently optimal for a broad variety of problems. Even more useful and good set of spherical codes, these are the spherical designs. And they're important mostly for stuff like numeric integration on a sphere, but an equivalent definition for them involves harmonic polynomials. So a spherical code we call tau design if for any non-constant homogenic harmonic polynomial of n variables, total degree at most tau, we have the sum of the values of these polynomials over all the elements of the polynomial to be 0. And naturally, if it's true for homogenic harmonic polynomials, we can extend to all of them. If instead of tau we put a whole set of positive integers, then the identity will hold only for the members of the set. For example, we can have a 1, 3, 4 design. We will look into 1, 3, 4 design in a bit. In order to study spherical codes and spherical designs from a more analytical perspective, we need to introduce this set of orthogonal polynomials called Gegenbauer polynomials. They are actually a particular case of Jacobi polynomials and can be introduced as Jacobi polynomials. However, we also have this simple recurrence relation for them. And it is very informative because from it we can see that the even members of this set are even functions, and the odd members of the set are, well, odd functions. In particular, the fourth polynomial is b-quadratic with respect to t. So we can present it as a quadratic function of t squared, which will also turn important in a little while. The reason why they're useful, they're so-called spherical harmonics and so on, is actually this addition formula due to Kortwinder. It connects them to the harmonic polynomials in this following way. And by this, it also connects them to spherical codes and designs, as we saw by the very definition. The main identity that forms this connection when it comes to bounds, the type of bounds that we call linear programming bound, is the following one. And it stems from just calculating in two different ways the sum of the values of this polynomial over the whole spherical code. On one side, we use Kortwinder's inequality. On the other side, we just split the sum between equal and unequal members. Using this identity, we can obtain a large number of bounds for the inner product, for the cardinality, and so on, spherical codes. And this, for example, is the general bound for such codes. When it comes to more specific bounds, we can frequently ease one of these conditions. For example, with antipodal codes, we don't need to be concerned with half of the coefficients, because the sum over all elements of the polynomial with antipodal codes is 0 due to sum of Gegenbauer's polynomials being odd functions. In particular, and this is what brings us back to the biangular line territory, we have this so-called relative bound for 5-distance antipodal codes. And we know that the 5-distance antipodal codes are also biangular lines. So if we have the following two conditions, which provides us with the necessary conditions for the different degrees of the polynomials in the addition formula, we can have this bound for the cardinality of a spherical code. And this can be proved from the main equality by setting this polynomial t squared minus s1 squared times t squared minus s2 squared. Here, again, to remind that plus minus s1 and plus minus s2 are the non-trivial inner products of the 5-distance antipodal code, and they correspond to s1 and s2 being the angles of the biangular lines. So in a recent article called Biangular Lines Revisited, Mikhail Ganzhinov and Ferenc Solushi, apologies if I've mispronounced the name, pay attention to many structures of biangular lines and to various ways in which biangular lines can be constructed, and indeed studied in their cardinality, both in particular dimensions and when n tends to infinity. But they also pose several open questions, and one of them is what happens if we have equality here and here. Do we have spherical codes or biangular lines for which equality in both places exist? And it turns out that the answer is no, as expected. With Petr Boivalenkov, we also studied such 5 distance antipodal codes in 2017, but we didn't focus on this exact boundary case. Kazhinov and Solzhenitsyn pointed it out, but also said that approaching this problem computationally would be somewhat unfeasible. Hence, here we provide an easy proof that clings on an observation about the values of the Gegenbauer polynomial in the inner products S1 and S2 squared. And in order to have equality in both places, actually, we need these 2 conditions. They are easily derived from the main identity, and in the first case, from just substituting the 2 equalities in the relative bound into one another. Note that apart from P4, we also have for P3, P1, and even P5 the same thing, the sum equals 0. So here we're dealing with 1, 3, 4, 5 designs, but we don't use the 5th degree at all. And in fact, it's 2k minus 1 design for all odd numbers. So the observation that allows us to solve this problem is that we have equality for the different spheric inner products. So if S1 squared plus S2 squared equals 6 over n plus 4, then P4n from minus S1 equals P4n from minus S2, and P4 from S1 equals P4n from S2. And this can be seen directly from the 4th Gegenbauer polynomial. Now, from this lemma and the second condition, we can calculate directly the values of the Gegenbauer polynomials in these inner products. And from the fact that P4n is quadratic polynomial for t squared, because it's an even polynomial the 4th degree, we can use Vieta's formulas for S1, S2, and we can obtain the following. But from this, we can also go back to the first condition, substitute there, and obtain directly this. And this only holds true for m equals 0 or n equals 1. And again, this is not something that a spherical code can have. Thus, no spherical codes with the desired property exist, and as Kazhinov and Sofia expected, and as it's usually expected in such cases where the bounds are too good to be true, no spherical codes with the design property exist. From here, one can probably proceed with some other interesting parts. For example, the question is what happens asymptotically if n tends to infinity. Shall we have something that will touch this bound? And this is an interesting question. However, we've yet to see if this can be done. I hope that we'll be able to do it in the recent future. With this said, thank you for the attention. And once again, congratulations on the 70th anniversary of Professor Drensky.
Thank you very much for the talk.
Dear colleagues, let's begin our afternoon session of the conference with the presentation of the Professor Azniv Kasparian from Sofia University, Konstantin. The subject of the presentation is the area of algebraic geometry. So please welcome Professor Kasparian for our talk. Thank you.
Thank you. I'm extremely grateful to my master's advisor, Professor Vesselin Drensky, for introducing me to research, for all the mathematical lessons he taught me and for his support. And on the occasion of his 70th anniversary, I wish him and all his family a good health, longevity, happiness, good luck and success in mathematics and all endeavors. I'm going to talk on a joint work in progress with Gregory Sankaran from the University of Bath. The topic is on the singular Galois quotients of a complex bielliptic surface by a finite biholomorphism group. Let's recall that the compact connected complex Lie groups of dimension 1 are the complex tori known as elliptic curves. Any elliptic curve acts transitively on itself by translations, and the entire biholomorphism or automorphism group of E is a semi-direct product of the translation group with the isotropic group of the origin. This isotropic group of the origin consists of the group automorphisms or the linear automorphisms of the elliptic curve. It's well known to be cyclic of order 2, 4, or 6. The correspondence associating to an automorphism of an elliptic curve, its linear part, is a group homomorphism whose kernel coincides with the translation subgroup. The finite translation subgroups have no fixed points on an elliptic curve, and their quotients are smooth elliptic curves. If a finite automorphism group has at least one non-translation element, then it has a fixed point on the elliptic curve, and the corresponding quotient is a smooth rational curve. For an arbitrary subgroup G of the product of automorphism groups of two elliptic curves E1 and E0, there are canonical projections of G on the corresponding components, which are group homomorphisms. Composing with the corresponding projections on the linear parts, one obtains two group homomorphisms with finite cyclic images. The canonical fibration of a product of two elliptic curves over its factors is equivariant with respect to the G action on the product and the action of the corresponding projection on the respective component. This amounts to the presence of following commutative diagrams for any entry of G, and implies the presence of canonical fibrations of the quotient by G onto the quotients of the elliptic factors by the corresponding projections. These canonical fibrations satisfy the following commutative diagrams with the corresponding Galois coverings. Roughly speaking, a smooth projective surface is minimal if a contraction of a rational curve results in a singularity. The holomorphic tangent bundle to a surface and its dual holomorphic cotangent bundle are of complex rank 2. The wedge square of the cotangent bundle is a line bundle known as the canonical bundle of X. The natural tensor powers of the canonical bundle are called pluricanonical bundles. The Kodaira dimension of a smooth minimal projective surface reflects the rate of the dimensions of the spaces of the global holomorphic sections of the pluricanonical bundles. If a minimal projective surface has no non-zero global pluricanonical section, then it is of Kodaira dimension minus infinity. if the dimensions of the global pluricanonical sections are bounded above by 1 and at least one of them is non-zero, then X is of codirected dimension 0. Now assume that X is not of codirected dimension 0 or minus infinity. And there is a positive real constant C such that the dimension of the space of the global holomorphic sections of the mth pluricanonical bundle is bounded above by the product of C and M for all the natural numbers M, then X is of codirected dimension 1. Finally, if X is not of codirected dimension minus infinity, 0 or 1, then it's of codirected dimension 2, and X is called a surface of general type. I will consider in detail the types of surfaces of codirected dimension minus infinity and 0, because in a while we shall see that the finite Galois quotients of a bielliptic surface are supposed to be of that codirected dimensions. A ruling of a surface X over a curve C is a fibration by rational curves. Any ruled surface with a rational base is birational to the projective plane and therefore a rational surface. The minimal projective surfaces of codirected dimension minus infinity are depleted by the rational surfaces and the ruled surfaces with irrational base. In order to distinguish the 4 types of minimal projective surfaces of vanishing codirected dimension, let's consider the space of the global holomorphic 1,0 forms on X. If this space is of dimension 2, then X is an abelian surface, namely a complex projective torus. If the space of the global holomorphic 1,0 forms is of dimension 1, then the surface X admits 2 canonical elliptic fibration, and that's why it's called a bielliptic surface. If X does not admit a non-zero global holomorphic 1,0 form, then it's a K-tree surface or an Enriquez surface, namely if there is a non-zero global holomorphic 2,0 form on X, then X is simply connected and it is called a K-tree surface. Otherwise, it is an Enriquez surface. Excuse me. Any Enriquez surface has sorry. Any Enriquez surface has a K-tree universal cover and a cyclic fundamental group of order 2. In 1907, Bagnere and De Francis classified the complex bielliptic surfaces. Later in 1976, Bombieri and Mumford extended their results to algebraically closed fields of any characteristic. Bagnere-De Francis theorem asserts that any complex bielliptic surface Y is a quotient of a product of 2 elliptic curves E1 and E0 by a finite group G without a fixed point. From now on, we refer to the group G as to the defining group of Y. More precisely, the defining group is either cyclic of order 2, 3, 4, or 6, or it is a product of 2 cyclic groups. The defining group has always a generator acting by a linear transformation of order D on the second factor and by a translation of the same order D on the first factor. Here, the integer d equals 2, 3, 4, or 6, because these are the only orders of linear transformations of an elliptic curve. The second generator of order 2 or 3 appears only when the fixed points of the linear part of the first generator on the second elliptic curve E0 are of cardinality at least 2. This second generator acts by translations of one and the same order t on both components. Recall that all the morphisms of a projective variety Y to abelian varieties factored through a unique up to an isomorphism projective torus called the Albanese variety of Y. The Albanese variety of a bi-elliptic surface is the elliptic quotient of the first elliptic factor from Wagner-Diffranchi's theorem by the projection of the defining group. So the name of the bi-elliptic surfaces originates from the fact that they admit two canonical elliptic fibrations. One of them is the Albanese morphism, whose all fibers are simple of multiplicity 1. The second canonical fibration has finitely many multiple fibers and a rational base. Any quotient Z of a surface Y by a finite biholomorphism group has Kodaira dimension, which does not exceed the Kodaira dimension of Y. We have seen that the bielliptic surfaces are of vanishing Kodaira dimension, so that their finite Galois quotients are of Kodaira dimension 0 or minus infinity. In 1990, Bennett and Miranda described the biholomorphism group of a complex bielliptic surface. Their result is incomplete because they overlook the dependence of the automorphism group on the isotropy group of the first elliptic curve, as well as on the stabilizers of the translation parts of the generators of the defining group in the corresponding isotropy groups. As a result, they claim that the normalizer of the defining group in the product of the automorphism groups of the elliptic curves E1 and E0 coincides with a corresponding centralizer. Last year, we noticed that this is not always the case. So there are cases missing in Bennett-Miranda's description. At the end of August 2020, Gebhard Martin published in Archive an article describing the automorphism group of a bielliptic surface over an algebraically closed field of any characteristic. The significant part of his work are the cases of characteristic 2 and 3, which are the most difficult ones, and the rest of the cases were reduced to Bennett-Miranda's result. The second version of Martin's article from June this year completes the classification of the automorphism groups of the bielliptic surfaces in characteristic different from 2 and 3. Few words about Martin's strategy for computing the automorphism group. First, he obtains the centralizer of the defining group in the product of the automorphism groups of E1 and A0, and then he computes the quotient of the entire automorphism group by this normal subgroup. As a corollary, Martin observes that the automorphism group of a bielliptic surface is the quotient of the normalizer of its defining group G by G. We approach the problem in a different manner, which we hope to provide a better description of the shape of the automorphism group. Our starting point is the liftability of the automorphism group of a bielliptic surface to the normalizer of the defining group. As a consequence, every group of automorphisms of Y lifts to a subgroup H of the normalizer and of the defining group, which contains G. We will describe the structure of H and N simultaneously as far as these two groups resemble to each other. Note that the defining group consists of elements with translation first components. That's why we construct a normal series of an arbitrary subgroup H of N, which consists of the subgroup of the entries with translation first components and of the translations from H. The projection on the linear part of the first component maps H onto a finite cyclic group. An arbitrary lifting of a generator of this cyclic group and the kernel H1 of the considered group homomorphism generate H. The order of the corresponding cyclic quotient equals the order of the linear part of any generator of this quotient. Similarly, the projection on the linear part of the second component maps H1 onto a finite cyclic group because the isotropy group of an elliptic curve is finite and cyclic. Now, an arbitrary lifting H0 of a generator of this finite cyclic group and the translation subgroup of H generate H1. In order to normalize the defining group, the second components of the translation group have to be fixed by the linear part of the defining group. The fixed point groups of the roots of unity on an elliptic curve are well known, and their cardinalities or their orders will be used for computing the number of the singular points of fixed multiplicity on a singular Galois quotient of a bielliptic surface. So far, we have a normal series of subgroups of H, which starts with an abelian translation group and has two finite cyclic quotients. Thus, H is a finite group if and only if its translation part is finite. In 2016, Yukihide has established that any smooth quotient of a bielliptic surface by a finite biholomorphism group is a bielliptic surface or a root surface with an elliptic base. The present talk discusses the singular quotients of a bielliptic surface by a finite biholomorphism group. Making use of the liftability of the biholomorphisms to the normalizer of the defining group, the problem is reduced to the classification of the singular quotients of a product of elliptic curves by a finite group contained in the product of their automorphism groups. A pair of automorphisms of two elliptic curves have a fixed point set, which is a product of the fixed points of the factors. If an automorphism of an elliptic curve has non-trivial linear part, then its fixed point set is finite and its cardinality equals the order of the fixed point group of the corresponding linear part. The non-trivial translations have no fixed points. This simple observation allows to classify the pairs of automorphisms of elliptic curves with a fixed point in the following three types. A pair of the first kind has non-trivial linear parts of both components and a finite set of fixed points. A pair of the second kind has an identical first component and a non-trivial linear part of the second component. The corresponding fixed point set is a finite disjoint union of elliptic curves parallel to the coordinate E1 curve. Elements of such type are called E1 reflections. Respectively, the pairs of automorphisms which fix point-wise a finite disjoint union of elliptic curves parallel to E0 are said to be E0 reflections. Independent works of Chevalier and Priel imply that reflections do not create singularities. In the setup under consideration, let a group H and a reflection sigma act on a product of elliptic curves and normalize a defining group of a bielliptic surface. If the H quotient is smooth and sigma normalizes H, then the group generated by H and sigma has a smooth quotient. The constructed normal series of H with cyclic quotients allows to find an element H0 with a translation first component and an element H1 so that H0, H1 and the translation subgroup of H generate H. The quotient A of the product of the elliptic curves by the translation subgroup of H is an abelian surface. The corresponding quotient Z1 by the normal subgroup of H consisting of the entries with translation first component is always a smooth surface. Let's denote by Z the corresponding quotient of the product of elliptic curves by H. Then the H-Galois covering of Z by the product of the elliptic curves factors to an unramified covering of the abelian surface A cyclic covering of Z1 which has no isolated branch points, and a cyclic covering of Z whose branch locus can have components of arbitrary dimension 0 or 1. In particular, if Z is singular, then Z should be different from Z1 because we know that Z1 is smooth, so that the group H is to have at least one element with non-translation first component. In fact, we show that this condition is not only necessary but sufficient for the singularity of Z. But before doing that, let's note that if there is a singular quotient Z of a bielliptic surface by a finite biholomorphism group, then the corresponding automorphism group of this bielliptic surface is to contain at least one automorphism with non-translation first component. Now, in general, the automorphism group of a bielliptic surface has a natural representation in the automorphism group of its Albanese variety. If the image of that representation does not consist entirely of translations, or saying it in a simple words, if at least one element of the automorphism group has non-translation first component, we say that the automorphism group of Y has non-translation Albanese representation. Now, let Z be a quotient of a bielliptic surface by a finite biholomorphism group, which leads to a subgroup H of the normalizer of the defining group. Then we show that Z is singular if and only if H contains at least one entry with non-translation first component. If so, then the automorphism group of Y is to have a non-translation Albanese representation, and the linear part of the defining group equals 2 or 3. The first cyclic quotient of the constructed normal series is of order K, which does not exceed 4 and is divisible by the order of the linear part of the defining group. For an arbitrary singular surface Z and an arbitrary integer K greater than 1, let's consider the set of the singular points of Z, which are of multiplicity K. Now, suppose that we are the usual setup and we have a finite biholomorphism group of a bi-elliptic surface Y, whose automorphism group has non-translation Albanese representation. We lift this finite biholomorphism group to a subgroup H of the normalizer of the defining group, and let's fix a lifting of a generator of the first cyclic quotient of H by its normal subgroup of the entries with translation first component. Now suppose that Z is singular and the group H does not contain a reflection. Then the resolution X of the singularities of Z is shown to be a K-tree surface or an Enriquez surface. Moreover, the linear parts of both components of H1 are of one and the same order K, which is divisible by the multiplicities of the singular points of Z. In fact, there are 5 possible cases for the resolution X of the singularities of Z, and the number of the singular points of Z of fixed multiplicity, and these cases depend on the orders of the consecutive cyclic quotients of the constructed normal series. If the linear part of the defining group and both cyclic quotients are of one and the same order 2, then the singularities of Z consist of 8 double points and their resolution is an Enriquez surface. In the remaining 4 cases, the resolution X of the singularities of Z is a K-tree surface. Moreover, the order K of the first cyclic quotient is divisible by the order 2 or 3 of the linear part of the defining group, and there are the following possibilities. If K equals 2, then Z has 8 ordinary double points. If K is 4, then Z has both singular points of multiplicity 2 and 4. There are 2 cases depending on the cardinalities of the singular points of multiplicity 2 and 4. And finally, when the first cyclic quotient is of order 3, then the singular locus of Z consists of 6 triple points. Now, if the linear part of that distinguished element H1 is of determinant 1, then the coset of H1 modulo the translation subgroup of H is a symplectic automorphism of the abelian surface A, and the resolution of the singularities of the corresponding quotient is a minimal K-tree surface, which is known as the Kummer surface of A of order K. In order to relate this Kummer surface to the resolution X of the singularities of Z, let's consider the blow-up B of A at the quotient of the fixed points of the coset of H1 or respectively of H1 squared modulo the translation subgroup. The product K of the translation group with the cyclic group generated by H1 is a normal subgroup of H with cyclic quotient. And let's denote by Z0 the K quotient of the product of the elliptic curves and put S for the K quotient of the surface B. If K does not contain a reflection, then its quotient by the translation group is a direct product of two cyclic groups. The corresponding Galois coverings map the abelian surface A on the singular surface Z and respectively the blow-up B of A on the resolution X of the singularities of Z. Because this Galois group is a product of two cyclic groups, the Galois covering has the Galois coverings, both of them have factorization in two cyclic coverings. The first pair of cyclic coverings are always ramified. If X is an Enriquez surface, then S is the Kummer surface of A of order 2, and the second cyclic covering is exactly the universal covering of X, so in particular, it's unramified. For all K3 surfaces X, this cyclic covering is always ramified. The considered setup exhibits X as a cyclic quotient of the surface S. Now, what's the relation between S and the Kummer surface? Here it is. S can be obtained from the Kummer surface of A of order K by a blow-up at a finite set of points, which is known explicitly and whose cardinality can be easily computed in any specific case. Now, concerning the existence of singular Galois quotients of bielliptic surface, for any bielliptic surface Y whose automorphism group has non-translation Albanese representation, we find examples of finite biholomorphism groups whose quotients Z have K3 resolutions of the singularities. If the defining group G has a linear part of order 2, then the automorphism group of the bielliptic surface Y has always non-translation Albanese representation. This is a consequence of the description of the entire automorphism group. And in all such cases, we find a singular finite Galois quotient Z prime, whose singularities are resolved by a minimal Enriquez surface. After describing the singular Galois quotients of a bielliptic surface of Kodaira dimension 0, we pass to the ones of Kodaira dimension -infinity. To this end, we exploit the canonical fibrations, which were earlier defined, and we defined them for an arbitrary quotient of a product of elliptic curves by a finite subgroup of the product of the corresponding automorphism groups. If the J projection of H consists entirely of translations, then the J canonical fibration has an elliptic base. Otherwise, it has a smooth rational base. All the fibers of the canonical projections are irreducible, possibly multiple elliptical rational curves, and when elliptic, the fibers are necessarily smooth. The presence of an EJ reflection in H turns the J canonical fibration into a ruling, while the presence of an 1 minus GA reflection in H creates multiple fibers. Now, bearing in mind this description of the canonical fibrations, one easily observes that if the lifting H of a finite biholomorphism group of a bielliptic surface Y contains a reflection, and if the corresponding quotient Z is a singular surface, then it's a rational surface. For any bielliptic surface Y with non-translation Albanese representation, we found examples of finite biholomorphism groups with singular rational quotients. If the linear part of a bielliptic surface, of a defining group of a bielliptic surface, is of order 4 or 6, then this bielliptic surface cannot have singular Galois quotients because its automorphism group has translation Albanese representation. Nevertheless, part of these bielliptic surfaces can be a resolution of the singularities of a ramified default cover S of a rational surface. This result is due to Miranda and concerns all the bielliptic surfaces Y with a cyclic defining group. The singular surface S can be obtained from the bielliptic surface Y by replacing 2 fibers of the Albanese morphism by appropriate reducible configurations of rational curves. And the default quotient R, which is a rational surface, is endowed with the structure of an elliptic fibration with a rational base. As a consequence of our description of the singular Galois quotients of bielliptic surfaces, we observe that any such singular quotient Z has a finite ramified cyclic Galois covering by a smooth quotient Z1, which is of the same Kodaira dimension as Z. Namely, if the resolution of the singularities of Z is a K-tree or an Enriquez surface, then Z1 is a smooth bielliptic surface. And when Z is a rational surface, then the first canonical fibration of Z1 is a ruling with an elliptic base. Now turn back to Yoshihara's result and note that his classification of the smooth Galois quotients of a bielliptic surface does not impose any restriction on the defining group of that bielliptic surface. And by explicit examples, one can see that any bielliptic surface admits a smooth bielliptic quotient by a finite biholomorphism group, as well as a smooth Galois quotient whose first canonical fibration is a ruling with an elliptic base. So all the cases of Yoshihara's classification do really occur for any bielliptic surface. And let me finish with a difficult open question, which asks for the characterization of the finite Galois quotients of bielliptic surfaces over algebraically closed fields of characteristic 2 and 3.
Hello, Professor Kasparian, for this very interesting, nice presentation, very attractive. I personally wish you success in publishing your major joint results.
Okay, very few words on the introduction in order to say that in the study of Jordan algebras, the structure of associative algebras with involution is extremely important. Similarly, when we study Jordan superalgebras, then we need to study associative superalgebras with superinvolutions. Here, the associative superalgebra means Z2 graded associative algebra. A superinvolution on associative superalgebra is a linear map which preserves the Z2 grading of our superalgebra. Alpha square is the identity, and moreover, alpha acts on the product of homogeneous elements A and B by reverting the order and put a sign, which depends on the homogeneous degree of the elements A and B. Okay, when we study associative algebras, we need to specify that the prime superalgebras with superinvolution at non-zero socle were determined in 1994 by Cuenca-Mira, Garcia-Martin, and Martin Gonzalez. And in a more natural way, Racine provided a theory of structure for primitive superalgebra by classifying primitive one with non-zero socle and superinvolution. Is a paper of 1997. On the other hand, in the theory of polynomial identities, the interest to superinvolution in superalgebras is twofold. The first one is the relationship with involution defined in algebras and the corresponding polynomial identities. The second one is the study of polynomial identities which take account of this additional structure. Okay. The first remark is that in the case of trivial Z2 grading, that is when the odd component is 0, then every superinvolution is in fact an involution. The second one is the following remark. When we have a pair of superalgebras, A and B, and we have superinvolution, alpha bar and beta bar defined on A and B, then we can define an involution on the graded tensor product. It is just the tensor product of the maps alpha bar and beta bar. On the other hand, when we study polynomial identities, we have three classes of associative algebras which play an important role. The matrices on the given field F, matrices on the Grassmann algebra E, and suitable subalgebras of matrices over E. We denote these superalgebras by the symbol MKL of E. More precisely, in characteristic 0, a variety of algebras is verbally prime if and only if it is generated by one of the previous algebras. It is a theorem of Kemmer in 8.4. So it's important to study involution and superinvolution in this kind of algebras. Here we consider the Z2 grading of the Grassmann algebra with even part is 0 and odd part E1. And so the elements of the superalgebras MKL of E are the following block matrices. A and D in the diagonal are with entries on E0, and the entries of B and C, which are rectangular matrices, are in E1, in the odd part. Okay, we can regard the previous algebras MK of E as the Grassmann envelope of a finite dimensional superalgebra. More precisely, we consider the matrix algebra MK plus L over F. We consider the elementary Z2 grading induced by the sequence of elements in Z2. We have K elements equals to 0 and L elements equals to 1. And so we have the superalgebra MKL over F. It is the same notation of the talk of Ioppolo in the morning. And the Grassmann envelope of the superalgebra MKL is the algebra MKL over E. Okay. These algebras are also of great importance in the quantitative approach to the study of polynomial identities introduced by Regev in the 70s, with the definition of the codimension sequence. So it is important to study for each of these algebra the following problem: determinant involution, the superinvolution, the generators of the corresponding star polynomial identities, the sequence of star codimension, in both cases corresponding to the existence in R of involutions or superinvolutions. Okay. In the finite dimensional case, the involution, the situation about involution is well known. When we consider matrix on the field F, we can consider the transpose involution T, and when the size of the matrices is even, we can consider also the symplectic involution. Here are the definitions. Moreover, when we have an algebra A, we can consider the opposite algebra and the direct sum of A with its opposite algebra. In this case, we can consider the exchange involution. We change the position in the pair, and this is an involution on R. When we start with a simple algebra A, then R becomes a star simple algebra. That is, any two-sided ideal invariant under the action of the involution is trivial. In some sense, the previous example are the only example of involution on finite dimensional star simple algebra. More precisely, when the field F is algebraically closed, then any finite dimensional star simple algebra is isomorphic to one of the previous algebras. Transpose involution, symplectic involution, exchange involution on the direct sum of matrices and its opposite. Clearly, A and B are isomorphic as algebras with involution if there exists an algebra isomorphism phi such that phi commute with the action of the involution on A and B. In this situation, we say that two involutions, star and diamond, on the same algebra A are equivalent if the corresponding structure are isomorphic as algebra with involution. With this terminology, the reflection involution theta, which is defined in this way, it is the flip around the secondary diagonal, is equivalent to the transpose 1. And when M is even, we can conjugate the reflection involution theta by this element V and obtain a new involution sigma, which is equivalent to the symplectic 1. Okay. In this way, we can remark that the algebra of M by M upper triangular matrices is a subalgebra of the full matrix algebra with respect to the involution theta. And the same conclusion holds in the even case with respect to the symplectic involution. Okay. In 26, Miko, Stoff, and La Scala proved that there are exactly two distinct equivalence classes of involution for UTM when M is even, and a single class in the odd case. They are theta and sigma. Okay. When we study superinvolution, the situation is similar but more intricate. A classification of five-dimensional star-symbol superalgebra is a consequence of Racine results. And we have the following theorem: if F is algebraically closed, then an infinitely-dimensional bar star-symbol superalgebra is isomorphic to one of the following. We have the previous superalgebra MKL over F with orthosymplectic or transposed superinvolution. We can consider also the exchange superinvolution at the exchange superinvolution when we start with MKL over F or Qn, and we consider the superopposite of this superalgebra. Okay. The transposed superinvolution is defined only for k equals L, and it acts on matrix algebra in the following way. And when we consider we define the superopposite algebra, we change the order in the product, and we put also a sign, and so to change the position in the pair produce a superinvolution on R. Okay, clearly we need to have the case of involution, and so we obtain the transpose when the superinvolution is orthosymplectic, k equals n, and the entry of the parties is 0, and also in this case. Okay, in 2018, Ioppolo and Martino gave the complete classification of superinvolutions defined on the algebra of upper triangular matrices. Once again, we have that there are exactly two distinct equivalence classes of a superinvolution when M is even, and just one class in the odd case. Okay. In the talk of this morning, and also in the talks of the previous day, the speaker recalled us that when we consider an algebra with an additional structure, it is important that it is possible to study polynomial identities which consider this additional structure. For instance, in the talk of this morning, we study H polynomial identities, but in my talk, we consider all the case of associative algebra and superalgebras, and the action is the action of involution and superinvolution. The main idea introduced by Regev in the ordinary case works in each of the previous case when we assume that the field is of characteristic 0. We can study the complexity of polynomial identities in terms of the behavior of codimension sequence. We need to consider all the free object, the admissible evaluation, the corresponding polynomial identities, the space of multilinear polynomials, the sequence of codimension, and its asymptotic behavior. Okay, is the table of the free object in the ordinary case, the case of involution, of superalgebras, of graded involution, and superinvolution. In each of these cases, we need a set of indeterminates, and we need an action or a degree when we study superalgebras or graded involution on superinvolution. And here we have a complete picture of the situations. We need also multilinear space. So Pn is the space, linear space generated by the monomial W sigma 1, W sigma n, where sigma is a permutation. But in the ordinary case, the indeterminates are all the xi, and we modify the value of W according to the structure we need to study. And so we have xi and xi star in the evolution case, y and z for superalgebras, y, c, and z is odd, graded involution, y and z, and also the image or under the action of the evolution, and the same in the case of superinvolution. In all of these cases, the codimension is given by the dimension of a quotient. The quotient is between the multilinear space. Here is the case of superalgebra with superinvolution, and so the notation in this talk is the following: Pn and Z2, which is the grading, and star bar, which is the superinvolution defined on the superalgebra R. And the second part, the factor, is the intersection of the multilinear space with the identity, the ideal of the identities. Okay, also in this case, we can consider the variety generated by superalgebras with superinvolution. The codimension of the variety is the codimension of the algebra. And in this case, we have this inequality. The star bar codimension sequence is between the codimension sequence and the codimension sequence multiplied by 4 to the n. So if R is a PI algebra, then also this codimension sequence is exponential bounded. In 2016 and 2019, Gian Bruno, Ioppolo, and Lamattina gave a characterization of varieties of polynomial growth by proving the following result. Okay, they assume that f is algebraically closed. Then V has polynomial growth if and only if V does not contain the following superalgebra. The direct sum of f with its copy is trivial gradient and exchange evolution. Some subalgebra M of 4x4 matrices upper triangular, and the involution is the reflection involution. Again, the subalgebra M with a non-trivial grading and the reflection involution theta. We know that in this case, the superalgebras are finite dimensional. Then we have also the Grassmann algebra with the Grassmann algebra E with its natural grading and identity map. It is a superinvolution due to the structure of E, and also the Grassmann algebra E, again with its natural grading and the parity automorphism pi. In this case, the odd part go to minus. We remark that the elements of M are matrices of the following type. We have the same elements here and here in this corner, and the same element B in this part of the elements. So when we have the reflection involution, then we act on A trivially and also on B trivially. In this, in the third case, the non-trivial grading of M is induced by this pair. And this means only that X and Y are odd, and the elements on the diagonal are even. And also, this is important, in the first three cases, the superinvolutions are actually involutions again. Okay. More generally, in 2018, Ioppolo proved that if R is finitely generated a superalgebra with a superinvolution which satisfies an ordinary polynomial identity over an algebraically closed field of characteristic is 0, then the limit of the n root of the codimension sequence exists and it is an integer. And it is the star bar exponent of R. Okay, so we can define a variety minimal if and only if for any trapezoidal variety U of V, the following inequality holds. And the problem is classify star minimal varieties in terms of their generating star algebras. Okay. We remark that in the case of algebras with involution, that is when the odd part is 0, then the codimension of R, we have this equality of the codimension sequence. In this case, Possino-Milles and Valenti proved that the exponent of any PI algebra without assumption on finitely generated case exists and it is an integer. More precisely, there exists constants C1, C2, T1, T2, and a positive integer D such that the following inequality holds. So clearly, the star exponent is D. So it is appropriate to characterize separately the minimal varieties of algebras with involution. We remark that the existence of the exponent for algebras with involution was proved in 1999 by John Bruno and Zaitsev for finite dimensional algebras, and also very recently result by John Bruno, Lamartine, and Possino-Milles, where they study also the polynomial part of the star codimension of R. We have the same exponent for the polynomial part T, and it is an integer or alpha integer. Okay. Again, the first result in the area and this area concern the finite dimensional algebras. By result of Silvia Boumova, this is equivalent to consider affine varieties. That is, varieties generated by finitely generated algebras with involutions. In this way, we can state that the affine variety V star minimal if and only if it is generated by this kind of algebra UT star A1 AN for some sequence A1 AN of finite dimensional star simple algebras. This consequence of few result of myself and La Scala and myself Spinelli 2011. Okay, let me say that UT star of A1 AN is a suitable subalgebra of the upper block triangular matrices UT D1 Dn Dn D1, where D1 Dn are the size of the star simple components A1 AN, and the involution on this algebra is the reflection evolution theta, which is defined on the full algebra matrices, on the full algebra NQD, where D is the sum of the size. Clearly, when we consider the star exponent of this algebra, we obtain the dimension of the semi-simple part, and so the sum of k from 1 to n of the dimension of the k, and we prove that the ideal of star polynomial identities of this algebra is an intersection of two products. The product in the given order from A1 to AN, and the product in the reverse order from A1 to an from 2a1. Moreover, okay, when we consider ut star of this algebra, we obtain the previous algebra with exchange involution, and also ut star of two copy of f with respect to reflection involution is the algebra M, which I defined above. This finite dimensional algebra was introduced in a different way by Mishenko and Valenti, and moreover, the algebras M and D characterize the varieties of polynomial growth. More precisely, Mishenko and Valenti and Giambrone and Mishenko proved that Cn star of V is polynomial bounded as algebra. If and only if the variety of algebras with involution generated by M and D does not belong to V, questa algebra. Okay, we have an accurate picture of the structure, that is generators, co-characters, and codimension in few cases. The variety are generated by the following algebras: 2 by 2 matrices over the field F, in both cases of simplet or transposed involution, is a result of Levichenko and Drensky and Giambrone. The algebras D and M, we have, okay, Mishenko Valenti and Mishenko Giambrone. We have some result about the case when the algebras are equal to the field F, is a result of me and Nardozza, and also this case we have just two components. The first one is D, and the second one is F. It is a result of me and Nardozza. Okay. In each of the previous cases, the study of polynomial identities is based on the analysis of the action on suitable linear groups on the space of the so-called proper polynomials and their generalizations. The space of proper polynomials appear in papers of Maltsev and Speck, and also in a paper of Volichenko, but their use in the study of polynomial identities of unitary algebras acquires greater visibility and take on systematic character thanks to the work of Vesselin. Okay. Finally, I would like to note that by using this approach, we determine the generators, the star co-character, and the star codimension sequence of the algebra M11 of E, with respect to the involution star induced by the pair of the transpose superinvolution in the matrix superalgebra M11 and the identity map E, IDE on the Grassmann algebra. So the action is the following. Okay, the new result are this. Me and Nardozza identified a class of algebra with involution that generate all minimal star varieties. We proved that V is a minimal star variety. If V is a minimal star variety, then V is generated by the Grassmann envelope G of A of a Z2 graded star bar subalgebra of M2D. We define A in this way. This superalgebra corresponds to a suitable sequence A1, AN of finite dimensional star bar simple superalgebras with the superinvolution. Again, we have the same property as in the evolution case. The ideal is the intersection of two products. Moreover, the grading is induced by an elementary grading on the full matrix algebra, and the involution of on GA is induced by the reflection superinvolution theta bar of M2D. Okay, the bridge to the study of a general case is provided by the following structure theorem for PI algebras with involution. It is a result of Aljadev, Jambrun, and Karasik. They proved that if R is a PI algebra with involution, there exists a finite dimensional superalgebra with superinvolution such that the star identity of R coincides with the star identities of G of A. The involution and the Grassmann envelope G of A is induced by the given superinvolution, the superalgebra A, and the superinvolution given by the parity automorphism pi. Okay. In the same paper, Gianbruno, Karasik, and Aljadev, Gianbruno and Karasik proved that there is a duality between the space of Z2 graded multilinear star identity of A and the Z2 graded multilinear star identity of G of A. In the first case, we have superinvolution. In the second case, we have the space related to the involution on the Grassmann envelope. And so we have a coincidence of the codimension sequence on this level. Okay, when F is algebraically closed, the exponent is a dimension of admissible subalgebra of maximal dimensions. Okay, we need the decomposition of A in the semi-simple part of the Jacobson radical, and we need this condition on the product of the components and elements of the Jacobson radical as bridge between them. Okay, in order to give some outline of the proof, the first step is a description of the transpose superinvolution from another point of view. We consider the map gamma, which give us, which needed to define the grading on M2K over F. We have an isomorphism as superalgebras between M2K and the grading alpha and MKK over F. The reflection involution is defined this way. And we have theta is a graded involution, and the matrix with respect to theta, the graded involution theta is isomorphic to the transpose involution. Now we modify theta by multiply some elements with the element epsilon ij. The value of epsilon ij is 1 or -1, and it is -1 if and only if the pair ij is in this product. So we obtain a superinvolution theta bar, and the structure M2K with theta bar is isomorphic to matrix algebra and transpose superinvolutions. Okay, the second step consists in the realization of each star symbol superalgebras as graded subalgebra of matrix, and I explain the general construction with the following example. Okay, for instance, we consider this subalgebra, superalgebra, M2 over F, and R is the direct sum of A and its superopposite. Okay, the grading on A is induced by 0, 0, 1. We reverse the order of the elements, 1, 0, 0. We add 1 to each element, and we obtain 0, 1, 1, 1, and we glue the sequence. Now we have this sequence, 6 elements, and so we have the superalgebra M6. And the grading is induced by this pair. Now we consider the corresponding reflection superinvolution, theta bar, which correspond to the set P of index 1, 2, and 4, which are the position where we have 0 in this sequence. Now, if we identify the pair A and B with the sum of these matrices, we have a monomorphism of superalgebras with superinvolutions. A similar result holds for superalgebras with transpose or orthosymbletic superinvolutions. In this case, we have just an element A, but we have again a sum of 2 elements, the matrix A0, 0, 0, and the image under theta bar of A star bar, and again it's a monomorphism of superalgebra with the superinvolutions. The final step is to glue the star symbol component in order to consider the elements in the Jacobson radical. Again, a simple example. We have 2 algebras, A1 and A2. The elements of A1 are 6 by 6 matrices. This is the grading. And the elements of A2 are 2 by 2 matrices with grading 0, 1. So we consider M8, and the grading is obtained by gluing the corresponding part of the previous sequence. So we have the part which corresponds to A1 in the beginning and the end of the sequence, and 0, 1 correspond to A2. The elements of the direct sum are matrices of the following type, and now we insert the elements of JI. Okay, we have here X and here Y, X a column and Y is a row. The set is P, the 0 elements, the sequence is 1, 2, 4, and 6. 1, 2, 4, and 6. And in this case, the even part of the Jacobson radical is generated by the following matrices, and the odd part of the Jacobson radical is generated by the matrices, the following matrices. Okay, clearly we can change the sequence and can induce the given Z2 grading. For instance, we can consider the sequence 1, 0. Now, in M8, the grading is induced by the sequence, the following sequence, and the set is 1, 2, 5, and 6. Okay, we obtain different algebras. Here is the okay, the dimension does not match, and finally, we can say that the role of G tilde and the definition of this superalgebra is clear. Is the sequence of the elements in the group Z2 that measure for each star symbol component the difference between the canonical sequence and the one actually used in the construction of A. The previous example, G tilde is 0, 0, because we have the canonical sequence in both cases, and it is the pair 0, 1 in the second one. Okay. Finally, when we come back to the study of finally generated PI superalgebra with a superinvolution, we can state the following theorem. If V is affine varieties of PI superalgebras with a superinvolution, then V is minimal if and only if it is generated by one of the previous superalgebras, Ut and the corresponding A1, AN, star simple algebras, the grading, the sequence which modify the grading on the radical, and the corresponding superinvolution theta bar. Okay, that's all. Thank you for your attention.
We also thank you, Professor Di Vincenzo, for your nice theorem presenting. Any questions on the talks are quite welcome.
Let me give some comment. First of all, I enjoy Alexei Kanel Belov. First of all, I enjoyed the talk, and I think it is very important to generalize of Gianbruno-Zaitsev type theorem with involution. And by the way, because of PI theory, we had a new insight in Grassmann algebra in many of this stuff. Of course, many stuff can be done in positive characteristic. And by the way, it's important subject also. It's very good to generalize Regev conjecture, something like that for all of this stuff. So I enjoyed the talk. Yeah.
Thank you very much, Alexei.
Some other questions? Let's take again Professor Di Vincenzo. Dear colleagues, let's continue with the talk by Professor Tony Pantev, Decomposition, Anomalies, and Quantum Symmetries. Please welcome Professor Pantev.
Thank you, thank you. Can you hear me?
Yes.
Okay.
See you.
Okay, right, great. Thank you. It's a great pleasure to have this opportunity to participate in the conference honoring Vesco's 70th birthday. I am really sorry I can't be there in person. I was hoping to be, but couldn't get away. Hopefully you can read my handwriting. I didn't have time to type slides, so I had to write them. I hope it's visible and readable. So I would like to talk about a story, which is really a story in higher algebra, but it's motivated by a question in mathematical physics. And so I would like to explain a little bit about the question and tell you what kind of algebraic problems it leads to and how we can actually solve those problems. So this is a joint work with physicist Eric Sharp, and it's about a phenomenon in quantum field theory called decompositions. And so I would like to explain a little bit what that phenomenon really is and talk about the mathematics behind it. And then the real story, which hopefully I'll have time to touch on at the end, it's how one can use these mathematical devices, which allow you to understand the composition in order to cancel anomalies in quantum field theory, anomalies which arise from secondary quantum symmetries and which are present when you have symmetries that act not effectively on the theory. And so I'll talk about the composition and dualities in the presence of anomalies. So let me start. So now it should work. So I don't want to go into the physics very seriously, but since the problems are motivated by the physics, I want to say a few words about it. So I want to review a little bit the background story on decomposition in quantum field theory. So what is this decomposition phenomenon? It's actually a remarkable occurrence, which tells you that certain quantum field theories that you describe in a geometric mathematical model happen to be secretly equivalent to sums of other quantum field theories, which tend to be simpler. So you start with some theory describing interaction of fields with some action functional, and on the surface of it, apparently the theory is just one entity. But if you analyze it closely, it turns out that that entity splits. And all the interactions are actually sums of simpler interactions. So that's the decomposition phenomenon. And in physics, it's to a large extent, traditionally, historically, it's an example-driven story. People just find those theories that decompose and analyze their pieces and get real information about the interactions in them. But in fact, it's this example-driven story. It has a background conceptual conceptual reason for existence, which is purely mathematical, and I'm going to talk about it. But let me just say the standard terminology is that this interesting quantum field theories that happen to decompose, happen to split, we say that they decompose. And the Saman quantum field theories in the decomposition are called universes. And I'm not gonna go in and explain why, but there is some real physics reason behind that. They represent actually different universes in the model. Now, what does the decomposition do for you? The space of the observables in quantum field theory, it's typically some space of linear geometric objects. So it's maybe some Hilbert space or maybe some family of Hilbert spaces with some gluing data, which arises from some geometry. And the datum of the decomposition, the mechanics of how you split that space of observables and fields into pieces is of course by using projectors. So you have this linear data, and there is a collection of operators, finite collection of operators, which are projection operators. Each of them squares to the identity. They multiply to 0, and they add up to the identity on the whole space of observables. And the interesting feature about the existence of those operators is something that you have to devise or prove in any particular case. But the interesting feature that gives you the decomposition of the theory is that on these spaces of observables or fields, there are these multilinear pairings that take a bunch of observables and collect them and produce a number out of them. And these multilinear pairings are actually decomposed in the pieces. So the pairing of a bunch of observables is a sum of the pairings of their projections by the projection operators. So that's one ingredient that you need in order to have a decomposition of the quantum field theory. And the second ingredient is that the partition function of the theory, which is what you get out of codifying the energy interactions. So it's some sum over states of an exponential of the energy functional or energy operator of the theory that also splits, and it splits of sum of exponentials of the different pieces. So you get actually a sum of partition functions, one for each of the images of the projectors. So that's the datum that you really need to have in order to have the composition in the theory. And the question is, where do these decompositions come from? And so they come naturally in two ways. One is that, so in general, quantum field theories mathematically are described by starting with some geometry. So you start with some manifold or some algebraic variety, or maybe some infinite dimensional manifold, or maybe something that has slightly more complicated structure, like a manifold modular symmetry group. And then you construct a space of fields and observables, which is some collection, as I said, of linear geometric data on that manifold. So it could be some collection of bundles, sections in those bundles, sections with values in differential forms, something like that. And then there is an action functional that describes the theory, and there are these correlators, which are these multilinear functions on the fields that produce numbers that are really measurable quantities in the theory. But so the lesson here is that there is a background geometry, which is a manifold or something like that. And then there is a collection of fields, which is bundles or sections of bundles or tensors or forms on that background geometry. And everything is described, the theory is described by writing functionals and multilinear functions on that space of fields. And the reason you have a decomposition is because the background geometry is disconnected. So if the background geometry that describes your quantum field theory happens to be a disconnected manifold that has several different components, then of course the fields have pieces on all those components, and all the interactions, everything decomposes. The projection to each connected component is what gives you the decomposition. So that's a very natural way to get decomposition in these theories. But also there is a more obscure and more mysterious way where everything is defined on a connected geometry. So we have a background geometry which is connected, and we have fields and observables which are geometric structures on that connected geometry. But then there are symmetries in the theory that we need to model by, or maybe remember them. And some of those symmetries act non-effectively. So that means that they act on the geometry non-trivially, but on the fields non-trivially, but on the geometry they act trivially. And it turns out that when you have this type of setting in the theory, you again have decomposition. So these are the two sources of decomposition that you see in examples in physical theories, both classical or quantum field theories. And so 15 years ago, Eric Sharp and I, we were studying these examples, trying to get some underpinning structure for them. And we realized that in all the cases where we could observe decompositions, either coming from gauge theories or from disconnected spaces, there was secretly a disconnected space in the background. So we made this conjecture saying that all the compositions of quantum field theories, in particular the ones coming from non-effectively acting symmetries, are actually coming from the fact that the quantum field theory is equivalent to a quantum field theory on a disconnected space. And so I'm going to talk about this conjecture now, and about some problems it leads to, and some interesting questions that one can answer. So this conjecture, so that was 15 years ago, and we did actually a lot of work on this conjecture, and many people followed. So the conjecture was verified in many examples of classes of quantum field theories. They're all so up until maybe 2 years ago, all the theories people looked at were two-dimensional quantum field theories with one-form non-effective reacting symmetries. But so the conjecture is verified for gauge linear sigma models, for non-linear sigma models. This is what we did originally. For orbifold sigma models, also something we did a little bit after we made the conjecture. For open string theories, this is something we did maybe 10 years ago. And then maybe 3 years ago, there was a big revival in the study of this statement. And now the conjecture has been verified in many more classes of theories. So Eric Sharp verified it for supersymmetric gauge theories. Then Sharp and Gwen, Tanizaki, and Unsao recently verified it for non-supersymmetric pure Young-Mills theories in the formulation of Migdal. And last year, Komargotsky and his collaborators verified it for adjoint quantum chromodynamics in 2 dimensions. So the conjecture has been verified for many two-dimensional theories. And in fact, starting from the work of Sharp and Komargotsky last year, now there is a generalization of the conjecture to higher dimensional quantum field theories, and people can actually prove it in many higher dimensional cases as well. I'm not going to talk about the physics, as I said. I just wanted to say that the physics is out there. But the conjecture actually has a lot of interesting consequences, some of which are purely mathematical. Already the original verification of the conjecture that we did for nonlinear sigma models gave predictions for disk instantons, for Gromov-Witten invariants in non-trivial manifolds with discrete symmetries. And these conjectures were, in examples, proven by us, and then in complete generality by Jiang and Tseng about 5 years ago. It gives non-perturbative constructions of phases in gauge linear sigma models. That's also something that people have been trying to do for a while, and one can use this decomposition to actually give those constructions. It gives explicit formulas for elliptic genera of orbifolds. So this is a recent work of Iger and Sharp. And it gives, so this is the part of the story I would like to say some words about. It gives cancellation of anomalies and computations of partition functions in anomalous theories. So this was something that was recently done in examples by Robbins and Sharp, and in our new work, the one I'm talking about, we actually did it from first principles in full generality. So, so I just want to say what the conjecture says in some concrete terms. So it can be made very explicit in the context of quantum gauge theories, as I said, with the setup in a group of symmetries which acts trivially on the background geometry, but non-trivially on the fields of that geometry. So this is a typical example of these decompositions. So here is the setup. You start with a gamma, which is a semi-simple Lie group. In fact, I should have said compact. It's either compact or algebraic, affine algebraic group. And then just to simplify the discussion, you need a finite normal subgroup which acts non-effectively, but I'll assume that that finite subgroup is actually in the center, so that I don't have to go into all sorts of complicated combinatorial formalism. I mean, it makes sense actually for any finite normal subgroup, but I'm going to talk only about central subgroups. And we have then some background geometry, which is going to be a space, typically a manifold, which is equipped with an action of the quotient of your semi-simple Lie group by the finite central subgroup. And the quantum field theories that we want to look at are quantum field theories for which the fields and observables are geometric objects on X, as I said, some kind of bundles, connections, possibly forms or tensors in the bundles with values in forms. And they are going to be equivariant, but they're going to be equivariant for the action of the big group, the group gamma. You see, only the group G acts on the base space, on the manifold. You can make gamma act on the base space, but then the central piece, K, will act trivially. But K will act non-trivially on the fields. So we are looking at theories for which the fields are described in terms of that background geometry, but the symmetries have this strange property that there is a finite group of symmetries that acts non-trivially on the fields, but trivially on the geometry, on the manifold. And so these types of quantum field theories are called gamma gauge theories with background X. And for such a theory, I'll write, just schematically, quantum field theory on X mod gamma, where X mod gamma is going to be understood as an orbifold or as a stack. And then the composition statement is that a quantum field theory, which is a gamma gauge theory on X with symmetry group gamma, with K acting trivially, is going to decompose. It's going to be a sum of quantum field theories on X which are G equivariant, but they're twisted G equivariant by some class that depends on characters of K. And that class is going to be a degree 2 cohomology class on the quotient X mod G with coefficients in the circle. And in fact, you can say what the class is. So the map from X to X mod G is the stack quotient. So this map is a smooth map. So you can consider it is actually a principal G bundle on X mod G, because this is as if G is acting freely. That's what the stackiness buys you. So you have this principal G bundle on X mod G, and there is an obstruction to lifting that principal G bundle to a principal gamma bundle. So there is some obstruction class which is in the second cohomology of X mod G with coefficients in the kernel of the map from gamma to G, which is K. And you can look at the image of that class under the character chi to get a degree 2 cohomology class with values in the circle. The character chi maps K to the circle. Just look at the image of the cohomology class under that map. And so that degree 2 cohomology class actually twists the fields. And the claim of the decomposition is that the quantum field theory on X, which is dealing with gamma equivariant fields and observables with trivially acting K, decomposes into a direct sum of a quantum field theory on X, which is dealing with fields and observables that are G equivariant, but not quite. They are twisted equivariant with respect, where the twisting is labeled by the degree 2 cohomology class. So that's the decomposition statement or the decomposition conjecture concretely for these quantum field theories, which are gauge theories. And this is the end of the physics discussion. So now I want to move to math and explain what's the mathematical content of that statement and how one proves it. Okay, so I'm going to switch gears now a little bit and work in algebraic geometry. You can work in differential geometry as well, but then you have to say more words, and I want to make the presentation simpler. So this algebraic geometry story is completely parallel, and the proofs are exactly the same as what you would do in differential geometry. So I'm just going to talk about the algebraic geometric statement. So we'll look at these quantum field theories, which are homomorphic and in fact algebraic, their background geometric data is algebraic and the fields are algebraic. This will be like complex algebraic objects. So the background geometry will be a complex algebraic variety X. We'll have a gamma, which is a semi-simple complex affine algebraic group. Omega chi, that twisting class that I was discussing, I'm going to view it now as degree 2 cohomology class on X mod G with coefficients in the invertible algebraic functions. It is the same thing. It is so X mod mapping to X mod G is a principal algebraic G bundle. And there is an obstruction for lifting that principal algebraic G bundle to a principal gamma bundle, which is a class in H2 with coefficients in K. And I want to push that class to a class in H2 with coefficients in the invertible algebraic functions by the character, which is a homomorphism from K to the circle sitting inside C star. So it gives you a map to C star and in particular to locally constant invertible algebraic functions. Okay, so now the basic mathematical reformulation of the decomposition principle for these gauge theories in the algebraic setting, algebraic geometric setting, is a theorem that we proved some time ago. And it's a theorem about sheaf theories. So it says that the sheaf theory of X mod gamma decomposes into a direct sum of sheaf theories on X mod G, but the sheaves on X mod G that you have to take for each piece of the direct sum are actually twisted. They're twisted by that cohomology class. And that's an actual mathematical statement. It says that the derived category of coherent sheaves on X mod gamma, which is nothing but the derived category of coherent sheaves on X, which are gamma equivariant, is a direct sum of derived categories of coherent sheaves, copies of coherent sheaves on X, which are G equivariant, but twisted equivariant with a single twisting for each character of K. So that's the theorem that describes the decomposition of all those gauge theories, quantum field theories, which are gauge theories for gamma with non-effective group actions. And I want to say a few words about the proof of that theorem. Maybe first let me talk about what the twisted coherent sheaf is. What is that twisting? So if you have an algebraic variety, which I'm calling script X, or it could be a stack or something like that, and you have a degree 2 cohomology class with coefficients in the O star in the invertible functions, then you can define a notion of an omega twisted coherent sheaf on X. So what is that? That's a collection of coherent sheaves and gluing maps. So this you need to choose an open cover. In fact, it has to be a nice enough open cover of X. And for each open, you need to specify a coherent sheaf on that open. And then on the overlaps of the opens, you have to specify isomorphisms of the coherent sheaf coming from the jth open to the coherent sheaf coming from the ith open. And, you know, if these isomorphisms composed correctly, if they satisfy the standard cocycle condition, then this data will describe just a global coherent sheaf on X. But we have this cohomology class omega, which is a 2 cocycle. You can think about it as Czech 2 cocycle for the cover with values in invertible homomorphic functions. And the twisted sheaf is a data like that for which these isomorphisms compose into a cocycle, but the cocycle is modified, is twisted by that cocycle, by that degree 2 cocycle. So it says that Gij composed with Gjk is not quite Gik, but it's Gik times an invertible homomorphic function, which is omega ijk, which is the omega given by this cocycle. And that actually gives you a good theory. You can define actually an abelian category of such guys, and you can derive it. And these are the omega twisted coherent sheaves on your stack. So in this statement here, this is what we're doing. We have a degree 2 cocycle with coefficients in the invertible functions, and we're using it to twist the shift theory on X mod G. And we have several different twistings, one for each character of K. And the claim is that the shift theory of X mod gamma is a direct sum of the shift theories, the twisted shift theories of X mod G with one twisting for each character. Okay, so how do you prove something like that? Yeah, I don't have that much time. Let me just, I'm gonna probably go fast through this. So it's a statement which is a version of Pontryagin duality or a Fourier transform, but it's a Fourier transform for groups which are shifted in a homotopical sense, in a homological sense, in one homological degree up. So here is what you do if you have a space or a stack S and an abelian group, which in my examples will always be finite. Then you have a constant sheaf of abelian groups over S, which I'm calling K underlined. And you can look at a stack over S, which is locally isomorphic to the classifying stack of that group. So it looks like S cross the quotient of a point by the trivially acting K. So that's what you would call a K-jerp on S. So that's an algebraic stack for which the stabilizers at each point are all the same, and they're all equal to K. So these guys are actually analogs in this world of stacks of or orbifolds of principal bundles. They are principal bundles over a commutative group stack, which is the classifying stack of K. BK consists of it's really the category of principal homogeneous spaces over K. And because K is abelian, you can tensor two principal homogeneous spaces over K and get another principal homogeneous space over K. So this category actually it's a tensor category with a symmetric tensor product. So you can think about it, and in fact, each principal homogeneous space also has an inverse. So this is actually a group category. It has a group structure as a stack. These guys Y, which are locally isomorphic to BK, are just principal bundles for that stacky group. And every such guy is classified, as usual, principal bundles with structure group blah are classified by degree 1 cohomology classes with coefficients in that structure group. So it's classified by a degree 1 cohomology class on S with coefficients in the group stack BK. And B is a delooping, it's a homological shift procedure. So this is the same as H2 of S with coefficients just in the group sheaf K. And if you have any such class, of course, if you have a sheaf of commutative group stacks, H1 with coefficients in that sheaf is the same as extensions from the constant sheaf Z by that stack. So every such class is represented by a short exact sequence of group stacks, Z, then some commutative group stack EY, and then the commutative group stack BK. And in fact, you can write down this EY explicitly as a stack is just the disjoint union of several copies, several stacks, which I call Y to the N for each integer N. And Y to the N for positive integers is just the tensor product of the principal bundle Y with itself N times. For N equals 0 is just the trivial principal bundle over BK. For n equals -1, it's the inverse principal bundle. Remember, BK is a commutative, so there is an inverse guy. And for a negative n is just the tensor product of n copies of the y to the -1 in the same way. So you get this space, and it actually has a natural group structure because you can take a product of these guys. And it naturally maps to Z because it has many different components, one for each integer. So that's what this UI guy is. And so the thing that allows you to prove this decomposition for the shift theories is the statement that any commutative group stack over S has a natural Pontryagin, or in this algebraic case, it's a Cartier dual, which is the stack of extensions from A to O star, or it's the stack of homomorphisms from A to the commutative group stack, which is the classifying stack of O star. So if you take this short exact sequence and dualize it in this sense, in this Pontryagin sense, you get another short exact sequence, the dual of Z, the dual of UI, the dual of BK. But you can compute the dual of Z and the dual of BK very easily from the definition. The dual of Z is actually the classifying stack of O star. And the dual of BK is the sheaf of groups for which the fiber is the group of characters of K. So now this UID is an extension of a constant sheaf of groups where the fiber is the group of characters by the classifying the sheaf of groups where the group is the classifying stack of O star. So this dual guy is a germ over the group of characters. This is a trivial sheaf of groups. It's just the product of S cross the group of characters. And there is a Poincare line bundle on the product of UI with UI dual over S, which is given by the universal by extension. And you can do a Fourier transform using that Poincare line bundle. You can take a sheaf on UI, pull it back, tensor it with the Poincare, and push it forward. And so a basic fact in this Pontryagin duality version of Pontryagin duality I'm talking about is that this Fourier transform is actually an equivalence of shift theories. So this is literally the Pontryagin duality statement. If you were doing it for groups, we are doing it for group stacks. So it's delooped once Pontryagin duality, but in fact it's proven in exactly the same way. And now you can decompose each of those. So this UI guy is disconnected, so it decomposes into pieces. The UID guy, its shift theory, also decomposes into pieces because it has a generic stabilizer, which is O star, and you can decompose by the characters of the stabilizer. And the characters of O star, which or C star, are Z. So for each integer, you get a component corresponding to sheaves on which the stabilizer acts by a given character. And one part of the Pontryagin duality statement tells you that the Fourier Mokai transform that identifies the shift theories matches components, matches the sheaves on the end connected component of the UI guy with the sheaves corresponding to the end central character on the UID guy. And applying it to the tautological character, the character n equals 1, this gives exactly the decomposition statement in the theorem. And finally, to get it to the setup of the quotients that I was discussing, you need to take S to be X mod G and Y to be X mod gamma and apply this whole thing to it. So this is the proof, and okay, I'm running out of time. So I'm gonna take 2 more minutes to try and tell you about the interesting story, which is what happens when you are dealing with these shift theories or these quantum field theories which have anomalies. So this is actually something that related to Vesselin's work tangentially, because these anomalies they correspond to symmetry groups or symmetry algebras acting which are non-associative, and the anomalies are measuring the defect to non-associativity. But the non-associativity is some kind of a new potent phenomenon in this case. So here is briefly what you do. You have a complex algebraic variety X, a semi-simple group acting, and we want to study these theories, quantum field theories or shift theories on X, which have an action, which are equivariant for the action of G, but the action of G is not an actual strict action. It's a weak homotopy action. It's an action up to homotopy. This means that the associativity condition for the action on the fields or on the observables doesn't hold strictly, but only holds up to homotopy. And there is an obstruction to these weak homotopy actions lifting to a strict action. And it is a degree 3 group cohomology class of G with coefficients in C star. So that's what in physics is called a global quantum anomaly of the theory. So there are many theories that you build which come to you with homotopy symmetries, homotopy associative symmetries, and they have these non-trivial anomalies. And the problem is that in these theories, or in the corresponding shift theories, the interesting quantities you want to extract, like correlators or partition functions, they're not well defined because of the anomaly. So you need to repair them somehow in order to be able to get measurable quantities, or in order to be able to get a good notion of a sheaf. And there was a fix that was proposed by Witten and then elaborated on and developed by Tachikawa 3 years ago of how to handle these global anomalies, which is to cancel the anomalies by enlarging the symmetry group. So the symmetry group acts by symmetries on the fields which are not strictly associative, but only homotopy associative. And what Witten and Tachikawa did was to say, okay, if you have this degree 3 cohomology class, you can erase it if you find some other group, bigger group, mapping subjectively on G, so that the pullback of the class vanishes in the degree 3 cohomology of the bigger group. Then you'll get a gauge theory for which gamma is the symmetry group. It doesn't act effectively because the kernel of the map will act trivially, but there is no anomaly. Everything is strictly associative. Everything is a strict action. And so Witten and Tachikawa actually solved this problem universally. They wrote for each degree 3 cohomology class a universal extension, in fact, a central extension, which erases the class. And now you can talk about the quantum field theory or the shift theory of this guy. The problem is that the relative correlators, which are the guys that are lifted from the theory with G symmetries, the sheaves with G symmetries, they're very special and they have additional structure. Sorry, I'm running out of time. So the goal is to understand these structures and mathematically refine the decomposition to incorporate them. And we could do it. So there are two theorems that we proved, which do the cancelled anomaly and do the decomposition in this setting. But it requires that the actual quantum anomaly, the degree 3 cohomology class, is not arbitrary, but it's coming from a quantum symmetry. It's coming from a degree 1 cohomology class with coefficients in K check by the second differential in the Linder-Hochschild spectral sequence. And I'm going to stop here and not formulate the theorems because I'm out of time.
Thank you so much, Professor Pantev, for this very important and integral lecture. Any questions of it? Welcome. Thank you. Are there questions? No questions. We thank you so much once again and wish you.
Thank you.
Dear colleagues, our lecturer is Professor Luis Rowen from Bar-Ilan University of Israel. It's my great pleasure to give the word to him. Thank you, Professor Rowen. Here we go. Thank you.
Thank you. It's a great opportunity to speak in front of this very important group at this conference. It's my honor to honor Vesselin Drensky, who's we saw during the course of the conference that his students have displayed a great variety of research interests, which they must have obtained from him. And Drensky is certainly one of the prominent algebraists of our generation. So I'm very happy to be able to be at this conference. Thank you. This talk is going to be on idempotence, which I heard a talk of Drensky on idempotence a year or so ago, so I think it's pertinent. Okay, so an idempotent is A squared equals A. And big A will be an algebra, which is not necessarily commutative. And we're going to assume that's non-trivial. So idempotent, as far as I know, one of the first uses of idempotence was by Peirce in the 2 centuries ago almost, where he had the well-known Peirce decomposition of an algebra according to idempotence. And even if one is not in the algebra, we're going to interpret 1 minus ax as x minus xa. Okay, so we have 2 left eigenspaces with eigenvalues 0 and 1 in the associative case. Now we're going to define the right and left multiplication maps in the obvious way, and they're eigenspaces. So we're going to view an idempotent both from the left and from the right. So we're going to look at A lambda delta as the intersection. And often we're not going to notate the idempotent A because it will be understood throughout the discussion. Okay, so we have these lambda delta eigenvectors and eigenvalues. So the Peirce decomposition looks like this. A00 plus A10 plus A01 plus A11. Okay, so some famous non-associative algebras are power associative and flexible, and they play an important role in this story. Commutative algebras are flexible because you can commute the elements and get x, y, x is x times y, x. And so actually we're going to be looking at commutative algebras and trying to generalize them to flexible algebras. On the other hand, if you have an algebra, one can define the Jordan multiplication. And in the power associative case, this remains idempotent, and idempotent remains idempotent. So Jordan algebras fit into this context. So Albert, a long time ago, Albert wrote a seminal paper proving that any algebra which is commutative and power associative decomposes as the direct sum of 3 eigenspaces, A1, A0, and A half. And furthermore, he showed that these eigenspaces interact. And this interaction of this sort is called a fusion rule. Now, people who've worked with, just about everybody's worked with graded algebras. Graded algebras are a kind of fusion rule. You have the product of the components going into a different component. So Albert's theorem shows that A has these fusion rules. And more generally, a fusion rule is a way that you multiply two components and you get a sum of components. And it's symmetric if the AG, AH, and AHAG wind up in the same product. And this relates to hypergroups, but I won't go into that. Okay, so here's some examples of fusion rules. The Peirce decomposition fusion rule is really a matrix grading, and it has this table. The Albert's fusion rule is very interesting. That's, well, you see it here, that the 0 component and the 1 component are orthogonal. That's why I have an empty set here. And 0 times half is in the half plus 1 component, and etc. And for Jordan algebras, this is very well known to Jordan algebraists. This is the way you get the decomposition into idempotency in Jordan algebra, where 1/2 is the extra eigenvalue. Okay, so this is all extremely classical. What do I do here? And you can view it in a slightly more general situation. An axis is an idempotent, which is semi-simple, and its multiplication operation is algebraic, satisfies a polynomial. So now, okay, so we have a left axis and a right axis, and we're going to combine the two. So an axis will be both a left axis and a right axis. But it also has this condition, that left multiplication commutes with right multiplication. Now, this is true in any flexible algebra by definition, because AXA is the same if you multiply first on the left or then on the right. But in general, we're not going to assume flexibility. So we're going to assume this axiom. So any axis has this decomposition into eigenvalues. And we're going to call that the decomposition. Okay. On the other hand, when you multiply on the left and on the right by A, you get a decomposition of this form, and they're the same. This space equals this space. And that's proved by Van der Monde argument. Okay. So from now on, A and B will always denote axes. And the only axial algebra, an axial algebra is generated by axes. And the only one with dimension 1 is obviously FA. So we'll start with dimension 2. And so AB has to be something times A plus something times B. And if you have delta and lambda, then you get this extra property if and only if delta plus lambda squared is lambda plus delta squared, which means that lambda is delta which is commutative, or lambda plus delta equals 1. You get flexible in either case, but you get a non-commutative flexible algebra in this case. So this is an example of a non-commutative axial algebra. So it's nice that there's a theory, at least, that's not commutative. Okay. So I did this. Now, in dimension 2, we had a complete description of the axial algebras in the last page. But when you go up in dimension, it becomes almost impossible without another assumption. So there's an extremely important assumption that the one, certainly A is in the one eigenspace, both left and right, because A times A is A. If you have nothing else except the multiples of A, then we say that the eigenvalue, eigenvector, well, that this is a primitive idempotent. And so we're only going to talk about primitive idempotents because it's extremely hard to say something about non-primitive idempotents. But it is a restrictive assumption. Okay. On the other hand, there's 0. 0 times A is 0. So technically speaking, you have the eigenvalue 0 also. So you're going to have, now often you have a non-zero eigenvector with eigenvalue 0. So we're going to write this decomposition. Y is something times A, because A is a primitive eigenvector, idempotent, plus Y0 plus all the other ones, all the other components. So this, please try to remember this. This decomposition we use throughout. And because of the primitivity, the y lambda I delta j will be 0 if any of the coefficients here is 1. Okay, so that's what you have here. So what's the simplest case you can have? Simplest case you can have is you have the 0 part, the 1 part, and one extra one, which on the left we call lambda, and on the right we call delta. So this we're going to call the primitive axis of type lambda delta. Is left side lambda, right side delta. And so this is decomposition of y. It has 5 pieces. Okay. Now, you might happen to have that these two components are also 0. Then we say the axis is Jordan type. And we'll say A has Jordan type if it's generated by axes of Jordan type. And Jordan type is actually the main focus of this investigation. First of all, if the algebra is flexible, any primitive axis has Jordan type. So that's one reason we want to look at them. So in general, a primitive axial algebra will be generated by a set of axes in which you have this decomposition into the 5 components. Now, this is a Z2 cross Z2 grading. Oh, I'm sorry. That's part of the definition, that this will be a Z2 cross Z2 grading of A. So where these show you the plus parts, plus, minus, plus, and minus parts. So this can be viewed as a fusion rule with respect to the grading. Okay. On the other hand, we can have different types, lambda and delta. These can be distinct. In the commutative case, lambda must be equal to delta, but they don't have to be. Okay, we're going to have a primitive axial algebra is n generated if it's generated by n axes. Okay. And when we have Jordan type, these two disappear and you just have this Z2 grading, where this is the plus part and this is the minus part. So the fusion rule is this. You have, well, you can just read it. This part times the plus part times the minus part is in the minus part. The plus part times the plus parts in the plus part, and the minus part times the minus parts in the minus part. Anybody who's worked with superalgebras, this is looked at this from a long time. So now we saw that Albert proved any idempotent in a commutative power associative algebra is an axis of type half. And this includes Cayley-Dixon algebras, which Alexei talked about in his lecture, and various generalizations. But the big push forward was in this 2015 paper by Hall, Rowen, and Spektorov, where they related axial algebras to the monster group and the Greece algebra and vertex algebras. So it's not completely fair because there are two eigenvalues, a quarter and 1 over 32. But their paper is only on one extra eigenvalue, but that also still includes Matsuo algebras and many interesting algebras. But they're not power associative. In fact, the third eigenvalue, or the extra eigenvalues, are usually not a half, or they're often not a half. There's a beautiful paper that deals with one that's a half. So first of all, anybody who's interested in this after the lecture should read Spektorov's exposition. Okay, that's on archives. But we want to look at this seminal paper in the non-commutative context. We want to see what you can say without assuming commutativity. So what's the difference? So primitive axial algebras for them are commutative with one extra eigenvalue. And they also assume that they have this fusion rule that the zero part is closed under multiplication. Now, you see, technically, it's the zero part plus the one part that's closed under multiplication. Now, this holds for Jordan algebras, but Albert, in fact, in his paper a long time ago, gave a counterexample to this property. But it was only for a single axis. It wasn't for an axial algebra. It was for, and it wasn't a primitive axis. So this is still an open question, whether this must hold. Okay, I'll get to that. Anyway, Albert dealt with the same sort of fusion laws, but nobody had called them fusion laws yet. So he called these algebras stable 50 years before people defined fusion laws. Okay, another kind of algebra which is of interest is a non-commutative Jordan algebra, A Jordan algebra is a non-commutative Jordan algebra which satisfies this, but a non-commutative Jordan algebra only has to be flexible. So every flexible primitive axial algebra has Jordan type. So this shows you that there's some interesting examples. And I don't know whether every primitive axiom algebra of Jordan type is actually flexible. I'll get back to that question later, because one can, in principle, it's known, although nobody's ever checked it out. So every principal axial algebra of dimension 3 is of Jordan type, and in fact, it's commutative except for one example. And so this is really the most important example in the theory, in the non-commutative theory, because it's an example. You have the span by these two idempotents and an extra element with these multiplication rules. Most of the time you get to y. Y squared itself is 0. And so the lambda delta component is fy, and the 0, 0 component is f times b minus y. I said that delta is lambda minus, here, and delta is 1 minus lambda. So A has type lambda delta, but B has the opposite type, delta lambda. So if lambda is different from a half, this is non-commutative, and it's different. What happened here? Oh, I can't. Okay, well, the idempotents I lost on the top. They're A plus beta y or B plus beta y. These are all idempotents. This has type lambda delta, and this is type delta lambda. And there's one more idempotent, which is an axis but not primitive, and it's A plus B minus y. So you can analyze this algebra very beautifully by using its idempotents. And something else of interest is that there's an involution. We learned about involutions today in many lectures, switching A and B and fixing Y or fixing C. It's the same thing. Okay, so it switches A and B and it fixes C. And I think this involution is important, but I haven't really had a chance to investigate it. Okay, now it's very easy. I think the people working in superalgebras have known, if they're old enough, they've known for 30, 40 years at least, that there's the automorphism sending the negative part to its negation. So y goes to y plus minus minus minus. And as I said, this is folklore for graded groups, graded algebras. But it was discovered in this context by Miyamoto, who used it to great effect. I mean, the fact that it's an automorphism is clear, but the fact what he proved, or what can be proved, is that when you take all the axes that generate A and take the automorphism applied to them, obviously is also an axis because the automorphism preserves all the structure of the algebra. So we call them Miyamoto axes. If you apply a Miyamoto automorphism to an axis, we'll call that a Miyamoto axis. And so if you have two automorphisms, A and B, if you have two axes, A and B, and take their Miyamoto automorphisms, they either commute or generate a dihedral group of order 6. This is in every case except when the extra eigenvalue is a half. So a half is bad in this sense. So, and in this case, the group of Miyamoto automorphisms is finite. If A is finitely generated by a finite set of axes, its set of Miyamoto in automorphisms is also finite. Okay, that is in the commutative case. That was in the HRS paper. In our setting, you actually have 3 Miyamoto automorphisms because the grading is C2 cross C2. Okay, so they coalesce for Jordan axes. But in the general case, you have 3 of them. And you also have this involution, okay. So I said this, when A is of Jordan type, you only have 1 Miyamoto automorphism. Okay. Here's a really important theorem. If A is generated by a set of axes, then A is spanned by the Miyamoto axes. In other words, the ones you get from X from Miyamoto automorphisms. This means that you can move from finite generation, like from affine, to finite span, finite dimension. Okay, that's, let's see. So we'll say that an NPAA is a primitive axial algebra generated by n primitive axes. And so using that theorem, you can reduce many questions about finitely generated primitive axial algebras to the 2 generated and 3 generated questions. So a question, well, are all finitely generated axiom algebras, are they of Jordan type? So we're in the funny situation where we have a theory and we have a nice theory for Jordan type. I don't know whether we have a theory for algebras not of Jordan type. And using that theorem in the previous slide, it's enough to check this for 2 generated algebras. And we have a theorem that every 2 generated algebra is of dimension less than or equal to 5. So you could put those on the computer and find out whether they're of Jordan type or not. But we haven't done that. We've trying to find some elegant way of looking at this. And we started looking at the algebras of dimension 4, and we think that those don't exist. But we think that there are of dimension 5. So here's an example. I won't spend much time on it. But here's an example which it looks like it's it's an example of dimension 4. But in the multiplication table, A is a primitive axis and B is an axis, but it's not primitive. Here's Here's A and here's B. And so we have two idempotencies, but it doesn't quite turn out to be an example. And in fact, we can prove that this particular kind of example does not exist. Okay, so I'm sorry if the conference were next week, maybe I would have been able to tell you more about that. So this is a question which I'd be very happy if somebody would be interested to look at. Then another difference in their theory is we don't assume that the axes have the same type. So we'll say an algebra is uniform if they're of the same type. And so there's something wrong. I can't get the top line here, but there's an extremely important question, probably the leading important question in this theory, whether finitely generated primitive affine algebras, primitive axial algebras are finite dimensional. So in this paper, they proved what they did is, since they have the structure of this group of Miyamoto automorphisms, they showed using the classification of finite groups that this is finite, and therefore the axial algebras are finite. But it entails classifying three transposition groups, and it's a huge problem, and it's not a realistic bound. I mean, the bound exists, but it's a huge bound. So Gorshkov and Staroletov showed that they have dimension at most 9, and that's the commutative ones, and the Jordan type ones also do. And so I expect that it will be true for all PAAs generated by 3 axes, but it's not clear. Then if we know about the 3 PAAs, then we'll know questions like this. Okay, the current method, their method and our extension of their method for analyzing PAAs is based on solving a system of linear equations in the eigenvectors. I showed you that the A to the I x, A to I y, A to the j correspond to the eigenvectors. And so you can build a system of linear equations with that and solve that for 3. But amazingly, before, you can't solve it. And there are too many equations. And so you need some other method. And I think there might be another method, but we're in the middle of this. Note that if you have an algebra, any algebra, which is finite dimensional, then you can embed it by the regular representation into an associative algebra. And we have the idempotence. Well, it's tricky. I won't go into this, but from the idempotence of the axial algebra, you get idempotence of the endomorphism algebra. And even though this is bigger, we have associative algebras. And I think there's a good chance that using associative algebras, you can prove that this is finite dimensional, and therefore this is finite dimensional. Okay, and I could give you the partial results that we have, but they're very technical. And so I thought I'd save them for this talk next month in the Brazilian conference. Anyway, this is the list of papers that these are all really important papers in the field, and well, I meant all the ones up to Hall, Sagan, and Spektorov, and well, again, wait, maybe I can get rid of the, yeah, good. So happy birthday, Vesselin, and best wishes for many more years. Thank you very much.
Thank Professor Rowen once again for your famous lecture. Indeed, let's open the discussion now.
Louis, may I ask about your three-dimensional example of non-commutative Jordan algebra?
Oh, it's not a non-commutative Jordan algebra. It's not a commutative axial algebra.
It's three-dimensional. It's not non-commutative Jordan?
Oh, it might be. Oh yeah, Yoav thought it is. Yeah, I never checked that out. It might be a Jordan algebra, right? Non-commutative Jordan algebra.
As I believe you mentioned that it is non-commutative Jordan. Well, but just I want to say, isn't it quasi-associative? Because an important class of examples of non-commutative Jordan algebras may obtain from associative, just like quasi-associative. You fix any scalar different from the half scalar lambda and define a new multiplication of elements A and B as lambda AB plus 1 minus lambda BA.
Oh, yes, that's, yeah.
Quasi-associative. It reminds very much me your example that it is quasi-associative.
Yes, Albert dealt with that in his paper, but he did that for power associative algebras. Yeah, that's certainly an interesting point. Just to clarify, it might in fact be a non-commutative Jordan algebra, but when I said of Jordan type, I meant axial algebras of Jordan type. They have this axis of Jordan type where it has these 3 eigenvalues, but that doesn't necessarily mean that it satisfies the non-commutative Jordan axiom. But they call it Jordan type in their paper, so therefore I also called it Jordan type. Or Yoav and I. This is all with Yoav Segev, by the way. I wrote that down, but I didn't say it.
Okay, thank you.
Thank you for the question.
Any other questions?
Does power associative mean that...
This is a question from the room, Professor Chipchakov.
Does power associative means that each element generates an associative subalgebra?
Yes, a commutative associative algebra. Right. Well, I guess it's obviously commutative. And so Albert was in line with what Ivan said. Albert had a way of improving the multiplication by this trick of taking lambda AB plus delta BA. And it might well be that actually the example that I put might be tied in with that. But as I said, what's really wonderful with the big advance past Albert, because Albert did so many things, but the big advance was by looking at non-power associative algebras, because then you could look at eigenvalues that are not a half. And that was, so that was the big step forward.
Thank you, Professor Rowen. We are really very appreciative to you. We will be back after 10 minutes pause. Thank you.
Okay, thanks.
All for coming. Thank you for bearing with me. Thank you for inviting me. I'm very happy to be here. And you can hear me?
Yes, so far, yes.
Okay, good. So I'm going to talk about a few papers of mine and a paper of Procesi that they're based on. The work is not tremendously recent, but in the last few years, I've had a couple of mathematicians who I respect tremendously who told me they didn't understand this work. So I thought this might be a good opportunity to talk about it. I'm going to spend maybe half the talk talking about Procesi's work from 1976, on which this is based, and then I'll show how this work generalizes to other verbally prime PI algebras. Okay? Okay, this is not a touch screen. I have to do something. Good. So the starting point is the double centralizer theorem. And I say that everything will be characteristic 0. In fact, that's an understatement. Everything will be over the complex numbers. It makes our life easier. And I like having my life easy. Whew, okay. So we start off with a finite dimensional vector space V. And I take V tensor n, the nth tensor power of V, V tensor V, n times. And I consider endomorphisms of this vector space. And there's two groups that act on the vector space in a very natural way. One is a general linear group, the set of endomorphisms of V, the set of linear transformations of V. If little g is in capital GLV, then it acts what's called the diagonal method. It acts on V1 tensor Vn by just acting on each factor. It's obviously an action. And then, of course, a symmetric group acts on V tensor n by permuting the vectors. So it acts on a basic vector by just permuting the vectors, for goodness sakes. So these two actions pretty obviously commute with each other. So if A is the subalgebra spanned by the elements of GLV, B is a subalgebra spanned by the permutations, they not only commute, but they have the double commutative property. If something commutes with A, it comes from B. If something commutes with B, it comes from A. Okay. And as a technical remark that we might need a little bit later, my office is kind of cold. Instead of this is a sort of a standard thing in Lie theory. Instead of the general linear group, you could also use the general linear, the superalgebra, where the elements act as derivations instead of the diagonal action. Okay, good. So that work goes back to Schur, it goes back to Weil. And in 1976, Procesi found a very nice way to apply it to invariant theory, although it might go back earlier to Sibiritsky, I'm not sure. So this double centralizer theorem has obscenely many applications all over the place, including representation theory, invariant theory, combinatorics. So recycling the letter, let's let A be the K by K matrices over the complex numbers. And I'm interested in which maps once a number of copies of A, polynomial in the entries, are invariant under simultaneous conjugation from the general linear group. In other words, T of A1 through AN is T of the conjugate of A1 through AN for any element of the general linear group. So by a standard technique in invariant theory, it suffices to restrict our attention to multilinear maps by things called specialization and linearization. Okay, so let's get a little bit more geometric. I don't know how to use these things. Okay, good. instead of GL K, instead of n by n matrices, K by K matrices, we'll consider the endomorphisms of a K-dimensional vector space. Instead of multilinear maps from n of V to the n into C, we'll just consider linear maps from the nth tensor product power of the endomorphisms of V into C. We're getting a little bit even more linear algebraic. We'll consider the dual space of the endomorphisms of V tensor n. And now here is the harder proof. It's a real blink and you miss it sort of proof. As a GLV module, the endomorphisms of V looks like V tensor V star, of course. And as a GLV module, V tensor V star tensor n looks like V tensor n tensor V star tensor n. Fine. And now, the GL invariance of the dual space of V tensor n tensor V star tensor n just looks like the GLV invariance of the endomorphisms of V tensor n. That last step might be marginally less obvious, and I'm not advancing to the next slide for some reason. Oh, what a snake bit. I just got myself a blank slide. Give me more blank slides. I don't want blank slides. Okay. Okay, so let's look at that last step, which is a little bit less obvious. How does V tensor n tensor V star tensor n star look like n of V tensor n? Given a endomorphism of V tensor n, we'll get a map from V tensor n tensor V star tensor n by the vector V tensor the vector phi goes to phi applied to T of V. Okay. Well, by the double centralizer theorem, this guy here, the endomorphisms of V tensor n commuting with GL, is spanned by elements of Sn. Okay. So let's try to trace it backwards. How does a permutation correspond to an invariant functional on endomorphisms of V to the n? Let's take an example. Let's take the permutation 1, 3 and fix this 2. So let's let our matrices correspond to elementary matrices, Vi tensor phi. Then sigma would take the triple A1, A2, A3 to phi1 tensor phi2 tensor phi3 acting on, and then you could permute, you put V3, you permute the V3 and the V1. So you have V3 tensor V2 tensor V1. So you get phi1 of V3 times phi2 of V2 times phi3 of V1. And here's the punchline. That's the same as the trace of A1, A3 times the trace of A2. So in general, given a permutation, if you write it as a product of cycles, you use a cycle decomposition, then it corresponds to the multilinear function. So the cycle A1 through AS gives you a factor of trace of A sub A1 to A sub AS. The cycle B1 through BT gives you the trace of A of B1 times up to A of BS. Obviously, it's invariant under simultaneous conjugation. And it's kind of nice the way that it's well defined, because when you write sigma, you could write the cycles in a different order and the traces commute. And within each cycle, you can permute the number cyclically, and you're allowed to do that in a trace also. So it works very, very nicely. And if you don't want just multilinear invariants, if you want all of them, you specialize, and you get their own invariant functions are given by trace polynomials, meaning products of things that look like trace of monomials. And this is called the first fundamental theorem, the FFT, for the general linear group. Okay. Application to generic matrices. Let Xij alpha be commuting indeterminates. Let capital X alpha be the K by K generic matrix. So it's a K by K matrix whose entries are these commuting indeterminates. If we identify Xij alpha with what's called a coordinate map on MKC to the N, then we identify the Ij entry of the alpha ith matrix. Then the GLV, let's take a look. For example, going back to 132, this is the sort of thing that's you do all the time in invariant theory. It's the sort of thing that makes my head hurt to think about. Let's take this map here. It corresponds to 132. If each A alpha is Aij upper alpha, then the map that takes, then the trace of A1, A3 times the trace of A2, with that thing there, the sum of the A alpha I times Aj I, the sum of the AII. In terms of coordinate maps, it'll be that thing which equals the trace of X1, X3 times the trace of X2. Namely, the GLK invariant maps are identified with what are called pure trace polynomials in the generic matrices, of which this is one example. So if you let R be the algebra generated by the generic matrices over the complex numbers, then the trace map takes R to the polynomial ring. The image is not a ring, but it generates a ring called the generic trace ring, often denoted C bar. And the general linear group acts on this polynomial ring by taking Xij alpha, the ijth entry of the conjugate of the generic matrix. And then the theorem says it's a trace ring, C bar, is equal to the fixed ring, and this is an easy consequence of everything we've set up to now. There's also a second fundamental theorem. In principle, there's higher ones, but everyone tends to stop at 2. So if you consider the action of Sn on V tensor n, this gives can be translated to a map from the group algebra of Sn to the endomorphisms of V tensor n. The first fundamental theorem identified the image as a centralizer. And the second fundamental theorem, the SFT, will identify the kernel of this map. So the group algebra of Sn is semi-simple. Of course, that's Maschke's theorem. And so it decomposes into direct sum of two-sided ideals. They're indexed by the conjugacy classes of the symmetric group. And these guys are partitions of n. So the group algebra is a direct sum of two-sided ideals indexed by partitions. Of course, there's nothing intrinsic about the identification, but there's a traditional identification, which I will assume uses Young tableaus. And then the kernel of capital F is a sum of all ideals with more than k parts, where k is a dimension of your vector space. Well, one important partition of height greater than or equal to k is 1, 1, 1, 1, 1, k plus 1 times. In fact, a partition has height greater than k if and only if it contains this one. Thanks to a wonderful little lemma proven by Puchesi and independently by Razmislov, this implies that all trace identities of k by k matrices are consequences of the one corresponding to this particular partition. And this identity is equivalent to a linearization of the Cayley-Hamilton theorem. So all trace identities of k by k matrices are consequences of Cayley-Hamilton. And as I hinted, this is also proven by Razmislov a little bit earlier, using rather different methods. Has an application also to co-characters. So if an element of the group algebra of Sn corresponds to a trace polynomial, then its conjugate corresponds to the trace polynomial gotten by permuting the variables. So it follows that the nth co-character of K by K matrices, I said co-character, the nth trace co-character of K by K matrices is the same as the character of the sum of the two-sided ideals of CSN, where lambda is a partition of height less than or equal to K, and under the conjugation action of Sn. And for each lambda, its character under the conjugation action of Sn is the inner tensor product, chi lambda tensor chi lambda. So chi lambda is the irreducible character corresponding to lambda, and you take the product or inner tensor product. So if we just sum these guys over all partitions with at most K parts, we get the trace co-character of K by K matrices. Okay, in sum, there's a map from the group algebra of Sn into the endomorphisms of V tensor N. If you know the image, you get the invariant maps, and you get the generic trace ring of the generic matrices. If you know the kernel, it gives you the trace identities and the trace co-character. Very, very nice. Okay, and now the point is, all this followed from the double centralizer theorem. Well, there's other double centralizer theorems, and some of them give parallel theories. And I'm going to be talking about the double centralizer theorems that have applications to verbally prime algebras. And if I have time at the end, I'll mention a couple others. So just in case anyone here doesn't know what a verbally prime algebra is, Kamer proved that every PI algebra has a nilpotent ideal, modulo which its PI equivalent to a direct sum of verbally prime algebras, which implies, well, that if you think PIs are important, the verbally prime algebras are also important. And Kamer proved that there are three classes of verbally prime algebras. Matrices over the field, we've been talking about those. Matrices over the infinite dimensional Grassmann algebra, and the Kamer algebras, MKL, which I will define momentarily. If you look at Z2 graded simple algebras of the complex numbers, there's two classes. One is you take a vector space with a Z2 grading, so it's V0 plus V1. And the endomorphisms of V, the linear transformations of this vector space inherit a Z2 grading, where the degree I part is the part, well, the degree 0 part preserves degree, and the degree 1 part reverses degree. And of course, since the endomorphisms of V is K by K matrices, whatever, it's a simple algebra. So it's, if you give it a grading, you get a graded simple algebra. The other class of graded simple algebras are not simple. It consists of two copies of the matrices, one in degree 0 and one in degree 1. So if you like its matrices over the complex numbers, adjoin U, where U squared is equal to 1. Well, let's take the former, the first one we're talking about. Okay. So in general, if you have a Z2 graded algebra, you form the Grassmann envelope of it. So you take the infinite dimensional Grassmann algebra A. That means it's generated by EI, where the EIs anti-commute with each other and have square 0. It has a Z2 grading with respect to which the generators are all degree 1, they're odd. So if you have a product of generators, if there's an even number of them, it's degree 0. There's an odd number of them that's degree 1. And then you form R0, or Z2 graded, tensor E0 plus R1 tensor E1. It's called the Grassmann envelope. And if R is simple, graded simple, this guy will be verbally prime. And all verbally prime algebras are equivalent to these. let me just remark, in Kramer's theory, the verbally prime algebras are only important up to PI equivalence. And hypothetically, there could be other ones than the ones we're defining here, but these turn out to be the ones, just the ones that work out nicely for the invariant theory and everything else very happily. Anyway, the verbally prime algebra you get here would look like MKL. It's all K plus L square matrices with entries from the Grossman algebra. When you break it up into 4 blocks, A is a K by K block, D is an L by L block, B and C are K by L and L by K. And the diagonal blocks A and D have even Grossman entries, and B and C have odd Grossman entries. And I call these Kramer algebras, and they have a nice trace function, where the trace of this matrix is the trace of A minus the trace of D. A and D have entries from a commutative ring. It's just the sum of the diagonal elements. And this function is a trace in the following 3 senses. It's linear over E0. The image lies in a commutative ring, and it vanishes on commutators. The trace of xy is a trace of yx. It's easy to prove. It's very nice. And of course, this last property implies that the trace of x is the same as the trace of x conjugate. So if G is an invertible element of MKL and you conjugate x by it, it has no effect on the trace. And it turns out that this algebra has an invariant theory, a trace identity theory, completely parallel to the case of K by K matrices, the classical case studied by Puccesi. The group of invertible elements in MKL is called the general linear Lie supergroup and is denoted by capital PL of KL. Fine. And there's also a general linear Lie superalgebra, which is a tad easier to work with. So we take away the Grossman algebra and we just work over the complex numbers. And we have the endomorphisms of this graded vector space in inheritance Z2 grading. And we give it the standard super Lie bracket. So if A and B are homogeneous, they're degree 0 or degree 1, their super commutator is AB either plus or minus BA. If one of them is degree 0, its minus is the ordinary Lie bracket. If they're both degree 1, if they're both 1, it's a Jordan product, AB plus BA. It's called a super Lie algebra, and it satisfies superversions of the basic axioms of the Lie algebra, such as the Jacobi identity. And there's a double centralizer theorem proven independently by Berele and by Sergeyev. And parts of the theory were also anticipated by 2 pairs of physicists, Bars and Balentikin and Dondi and Jarvis. Okay. So you take a graded vector space with graded dimension KL. Yeah. We form V tensor N, and there's 2 things that act on it. The symmetric group acts with sign permutations. So if V1 through Vn are homogeneous and you permute them, you get the permutation with a plus or minus sign. And the way this sign works is odd vectors anti-commute. So you count how many degree 1 vectors are permuted and you give it a plus or minus sign. The super Lie algebra acts by signed derivations. So if T is homogeneous and V1 through Vn are homogeneous, then you get the sum of, it looks like the ordinary derivations with plus or minus signs. The signs work that if T is degree 1, you count how many degree 1 elements it jumps over. The philosophy is degree 1 elements anti-commute, and you give it a plus or minus sign. And of course, use linearity to extend it to O of PLV until V tensor N. The 2 actions commute, and they have the double centralizer property completely analogous to Shor-Weil duality. So in order to apply the double centralizer theorem to capital MKL, we have to basically tensor with the Grossman algebra. So we could have the notion of an E space with greater degree. We have a notion of a tensor product over E. The details are not difficult, but I'm going to ignore them, of course. And then any E map from V tensor n to V tensor n that commutes with capital PL comes from Sn. So there's an invariant theory result. If you take n copies of MKL and you map it to E, and you say they're polynomial and the entry is appropriately defined. And if it's invariant under simultaneous conjugation from capital PL, then it comes from, then it's a trace map. You can define generic matrices. It's pretty easy. They're K plus L by K plus L matrices. The elements of capital A and capital D are Tij alpha, ordinary, polynomial sorts of things, commute with each other. Elements of B and C are Grossman things, Eij alpha. They anti-commute with each other, commute with the Tijs, and of course have square 0. And you can have PL act on the supercommutative algebra via G of, we'll call it X. It could be a T or an E. Ij is the Ij entry of the conjugate. And the fixed ring is generated by all traces. And there's a technical issue. You can use either the general linear group or the general linear Lie superalgebra. If you use a superalgebra, you don't have to go up to E, you can just use C. But if you want to use capital PL, then you have to worry about introducing new Grossman elements, you have to use E. Okay, we can live with it. Okay, and there's a second fundamental theorem. If I'm calling it phi for some reason, takes the group algebra of Sn into the endomorphisms of V tensor n, using the sign permutations, via graded vector space dimension KL. And the kernel is going to be direct sum of two-sided ideals, of course. And the kernel will consist of two-sided ideals corresponding to partitions with more than K parts, each greater than L, which means L contains, the lambda will contain lambda 1 plus 1, K plus 1 times. Sometimes called the hook theorem. It looks like this. Here's a picture which is called the K by L hook. The first K rows can be as long as you want. The remaining rows have to have size L or smaller. If lambda is inside the hook, then it's mapped isomorphically by phi. If lambda is outside the hook, then it's mapped to 0. It's in the kernel. So as in the classical case, knowing the kernel lets us determine the pure trace identities of MKL. If A is an element of I lambda and it corresponds to a trace polynomial F, it's a trace identity if and only if lambda does not lie in the K by L hook. So that implies that all trace identities are consequences of the minimal identities. The minimal ones have degree, K plus 1 times L plus 1. And all trace identities are consequences of those coming from that particular diagram. We can also talk about the trace co-character. It would equal the sum of chi lambda tensor chi lambda, summed over all lambda in the K by L hook. And these identities were somewhat investigated by Cantor and Trishan in the late 1990s. Okay, well, I'm going to 20 after, I think. Okay, I'm not going to finish, but I don't care. So that's how things stood for a long time. MKL is kind of similar to matrices. You set L equal to 0, you get something PI equivalent to matrices. And for years and years, I wondered if you could generalize this to n by n matrices over the Grossman. The problem is it doesn't have any natural trace function. And one way around it is to use supertraces instead of traces. So MNE has a C2 grading. We can make a supertrace just by taking the sum of the diagonal entries. That means that if A and B are homogeneous, the trace of AB is plus or minus a trace of BA. It's not so bad. I studied these in 1994, but that's not what I'm talking about today. We're talking about some newer work. It turns out there's a function from MNE to E where you take the degree 1, the odd part, of the sum of the diagonal entries. And this is called a queer trace. And here's a sense in which it's a trace. Here's a sense in which it's not a trace. It's linear over A, and the queer trace of AB is equal to the queer trace of BA. It vanishes on commutators. But obviously, since the image is in E1, the queer trace is anti-commute instead of commuting. So you can't use the symmetric group to model these things. You have to use something else. And it turns out that back when Sergeyev proved his double centralizer theorem for MKL, he also proved another double centralizer theorem, which turned out to be exactly what was needed to get the invariant theory and everything else for matrices over the Grossman. So this is going to take a little bit of work. We'll start with the Clifford algebra. It's generated by C1 up to CD. They anti-commute with each other, but unlike Grossman variables, each has square equal to 1. Okay. So symmetric group SD acts on the Clifford algebra on these D generators by permuting the generators. And the Sergeyev algebra is a twisted product. So it's called WD, I guess, and it's generated by permutations and by C1 up to CD with relations. The CIs anti-commute with each other, have square 1. And if you conjugate one of the CIs by sigma, you change it to C of sigma vi. Your basic twisted product. And that'll be one side of the double centralizer theorem. The other side is the queer superalgebra. The name queer comes from physics. It has something to do with elementary particles, I think. And QN can be defined to be the sub-superalgebra of PLNN consisting of all matrices ABBA, where the block elements, the block off diagonal elements are respectively equal. Equivalently, it's two copies of general linear group, one in degree 0, one degree 1, with this degree 1 element with square 1. The equivalence being that the matrix corresponds to A plus B. Okay, so let's let U be a graded vector space with the degree 0 part and the degree 1 part having equal dimension, say n. More concretely, say U0 has basis U1 through UN, and the degree 1 part U1 has basis U minus 1 up to U minus 1. And we're going to need an isomorphism between U0 and U1, let's call it J, which takes UI to U minus I and vice versa. So QN can be thought of a little bit more geometrically as elements of PL and N, which commute with J. Now, each of WD, the Sergeyev algebra, and the queer algebra, queer superalgebra, act on U tensor D. The action of QN, well, PL acts, so this is just a restriction, acts by super derivations. As for WD, I have to tell you how permutations act and how Clifford elements act. Permutations act like they used to act as sign permutations. They change the order of the entries and give you plus or minus signs. And CI takes a tensor and multiplies the ith factor by J. It switches UI to U minus I to UI with an appropriate sign, namely CI is a degree 1 thing and jumped over the first I minus 1 things to get there. Okay, very good. So we have actions of the Sergeyev algebra and the queer superalgebra, and we have the double centralizer theorem. That's what Sergeyev proved. Okay, very good. Oof. If we tensor with E, you can prove that all GL and E invariant maps from MNE to the KN to E are queer trace maps, are products of queer trace monomials, analogous to trace polynomials. You can do generic matrices also. You let capital Xi have ij entry, Tij alpha plus Eij alpha. So they're generic Grassmann elements. The T's commute with everything, and the E's anti-commute with each other and have square 0. Then you could form the algebra generated by these generic matrices. Queer trace would take it down to the supercommutative ring generated by the Ti alpha and the Ei alpha. The image generates a subalgebra C bar. And this C bar is the fixed ring of G, L, and E acting on the Tijs and the Eijs. So, okay, and Qn can be realized two ways. We'll use either as GL plus GL, or as a subalgebra of PLNN, and they each have invariant theory applications. And I think I'm out of time, so I'm going to stop here because it's a terrible crime to go over. Thank you very much for coming to my talk, and I'm really sorry about all the difficulties I had.
Thank you, Professor Berele. Indeed, the discussion is now open.
Alan?
Hi.
That was a really beautiful talk. Can you conclude things about identities of Mn of E from this theory?
Yes and no. There's a little difficulty. There's a personal difficulty that I have, which is this: for FSN, I understand what idempotents look like. For the Sergeyev algebra, there's books about it, and I just can't wrap my head around it to understand it well enough. I do know one. Here's something that I was really, okay. So I wrote a paper about this with my colleague, Stefan Katoyo. We looked at the one variable identities for MNE. And MNE satisfies this queer trace identity, this product of queer trace of X times queer trace of X squared going up to queer trace of X to the n plus 1 has to always be 0. And we proved this using the representation theory of the Sergeyev algebra. And I think it's very likely that there's a neat algebraic proof of it. If it's a shame to have a talk without ending with some open problem for people to work on.
Oh.
I know that thanks. Also, the kernel is known, and the minimal, and it's, yeah, very good. So if you're looking at n by n matrices over the Grassmann, the degree of minimal, the trace identity of minimal degree has degree n plus 2 choose 2, and there are consequences of the ones of that degree. And I'll tell you what, as long as this is a conference for Drensky, let me mention some other theorems that use invariant theory, because one of them is due to Bakhtarian and Drensky. They use invariant theory to identify the identities and co-character of bilinear maps, which has application to great identities of matrices. Other applications are to the invariant theory, the traced identities of diagonal matrices by myself and Megdev, and Domokos, who will probably talk about it tomorrow, who used a double centralizer theorem of Amitai to study block diagonal matrices.
Thank you. Some other questions?
And then I'll give you another question you can work on if you like. Bakhtarian and Drensky, their theorem is based on, well, basically the invariance of the symmetric algebra of a tensor product. Why not do the exterior power? Why not try to do the Z mod 2 Z graded? So here's something else you might want to work on if you want something to work on, is try to find a Z2 graded version of the Vesselin Drensky results. Might be possible, might be interesting.
Well, let's close discussion now. We'll be back after 15 minutes.
Well, let's start our last session for today. Our first speaker is Rumen Dangovski from the Massachusetts Institute of Technology. And his talk is dedicated to, is devoted to algebraic structures in deep learning.
Okay. Well, thank you for this introduction. Hello, everybody. It's a great honor to present today in this conference dedicated to the 70th anniversary of Professor Drensky. I would like to express many thanks to Professor Chipchaku for inviting me to present today. And I will talk about the topic that is not very common in this conference, but I hope that by the end of this talk, you share my enthusiasm for my current research, and hopefully I can get some of your thoughts. But first, I would like to share more about my research journey and how it fits in the context of this conference. So a lot of members, I have interacted with a lot of members in this conference already. My first steps in research were with Konstantin Delchev back when I was doing math competitions and conferences in Bulgaria. So he gave me very useful guidance back then. And then I was very grateful to be able to work with Professor Drensky and Professor Funduk. We wrote 2 papers together on Weizenbiot derivations of free Matabelean Lie and associative algebras. Then I continued my exploration in the field of algebra. I did a project on the maximal containment of lower central series ideals. And then I was very grateful to be able to present this work in Professor Horozov's seminar at Sofia University. After that, I worked with high school students, so I tried to pass the torch, and Chavdar Lalov, he was actually from my first math school back in Pleven. We did the project on self-avoiding walks on lattice strips. So I find it very, so after this, I continued to study math and physics at MIT. And now I work in this field of deep learning, which I can't really say that this is science yet, but we're still trying to come up with the building blocks to make it a science. And we'll discuss more of that in depth in the next few slides. Yeah, I find it very interesting that all of these people are members of this conference. So let me just give you an outline of what I plan to talk about today. So I will show that structures are really the key component that makes deep learning work. And we'll explore 2 different types of baking in structure into the models that we're playing with. So one of them is going to be invariance, and the other one is going to be equivariance properties. But first, let's begin with discussing what the structure might be. And for this, I'll just try to define the problem of deep learning. So we want to take data. So this could come in the form of pictures in your computer. So for example, imagine a picture of a mug. And we want this data to represent it with numerical features. So usually the way we store our pictures on the computer are in the form of images, RGB images for red, green, and blue. So the values of the pixels themselves can be a numerical representation. We'll see that this is not the best way to represent data. And there's, in deep learning, what we want to do is we want to take these images and we want to have a parameterized function that can map the numerical features of the input to a decision, to a prediction of whether there is a mug on the picture or not. And the way we measure success in deep learning, and this is the part that makes it very difficult to claim it's true science, is that because the problems that we have, it's not very clear what the best features are to learn here are. So the only thing we can do is we can just measure the performance of our mathematical function on a test set. So I can take another mug that I haven't seen during the tuning of the parameters of the function, and then I can ask how good the prediction is. So a central question is what features to choose for that mug. And there are certain useful properties that we can require. So for example, I know that this object is the same mug if I translate it in the image, or I can change the color of the mug. I can look at a different color of the mug, or I can even look at a different scale. So I can have a zoomed in version of the mug. So all of these three things, we want the mathematical function to say that it's the same class, a mug. And the question is how to achieve that. So traditionally, what deep learning has been doing is to take a collection of a lot of examples. So imagine a data set of 1 million images from the internet, and people to annotate these images, to tell what is on the picture, and then having a lot of examples and a lot of annotation, a lot of human labor. We can fit the models. The models can discover the desired structure. For example, they can discover that it doesn't matter where the mug is; it's still the same thing. So this is very costly because human labor doesn't scale. So the question is, can we come up with something more useful? And for this, the answer to this question is yes. And I'll try to convince you today that how we can do this. But let's think about what is our background knowledge. Basically, so far I've shown you some types of invariances that we would like to require in our model. We would basically require that the prediction to be the same no matter where I translate the object in the picture, and no matter what color it is, we want it to be the same thing. So the question is how to bake that information into the parameterized function that we are learning. So what this parameterized function is here I will break it down into different components. First, we have the red, green, blue image. So this, you can think of this as a tensor that has 3 channels for color. And then depending on the resolution that we want, we can have different size of that tensor. But our input image in the very raw form it looks like this. And then what the model is, we have 2 components. One of them is an encoder. This is the deep part that takes a high dimensional tensor, and through a composition of different functions, it brings the numerical representation, the numerical features into a vector space of lower dimensionality. And then once we have this deep part, we're going to have a linear classification on top of these features. So you can think that once we reduce the features to be 512, we can try to find what the best linear combination of these features is in order to make the predictions in the optimal way. So the challenging part, the part that we will focus today is how to construct that encoder F. Let's see what are the approaches that we will explore. So we have the first approach is to constrain the parameterization of the function such that we can have the desired invariance of that function. And the difficulty of this thing is that once we constrain it, it's hard to optimize such a function. So the optimization methods that we have to configure the parameters, they're not working so well when we have a funky constraint of the parameterization. So I'm going to show you a second approach that relaxes the constraint. So and just guides the optimization process to arrive at to incentivize an invariance of the parameterized function with respect to the transformations that we require. So the pro there is that this is easier to optimize, but the con is that the property is not guaranteed in theory. So let's jump into the first approach, and here is where the structure that I'm talking about appears. And the first approach is basically thinking with respect to the geometry of the images that we have. You can think that the images that we're considering they're signals on an infinite lattice, and then this infinite lattice, we'll call this to be the domain omega. So I'm abstracting this because in deep learning we don't only have pictures, we have graphs, we have different kind of structures that have the same, that could be described in the same formalism. So the domain omega is our lattice, and each geometric domain comes with a group of symmetries. And the signals, let me try to define the signals now. So the signals are the actual data that we observe, and here, like for the collection of signals on the domain omega, this is just a collection of functions that are mapping the domain into a vector space, which is isomorphic to the, in our case, to these tensors that we were looking at above. So these are just the raw values of the pixels. The action of the symmetry group on the domain induces an action on the signals, because the signals themselves, they form a vector space, and we can study the representations of the groups of symmetries of the domain into the input space. This action is a very useful structure that can guide the modeling of the parameterized functions that we have. Another property that I would like to discuss, which we've seen in the beginning, is that the notion of scale separation is also very important. So because we start from something very high dimensional, we would like to gradually reduce the dimensions, but we would like to maintain the information. So if I take a finer domain omega, a finer grid, and if I coarsen the grid to get something that I would get an image that is more pixelated, and the quality will be worse, but I would require the prediction to be the same. So the composition of a coarsening and a function that I train on that coarsening should give the same result as if I started from the finer lattice. And this is the blueprint of building models that basically take advantage of the group action of the different layers of the functions that we are composing. So we have different types of layers. So we have equivariant layers. Why is it important to have equivariance? And actually, what is equivariance in this case? Well, you can think in terms of computer vision tasks, which is what I'm showing you right now. Sometimes we want, if we change the input in some way, the output of the parameterized function to change in a corresponding way. So for example, if my goal is not to decide whether there's a mug or not in this picture, but if my goal is to segment the picture, if my goal is to segment the mug, for example, my goal is to say where the mug is on that picture in front of you, then I would require an equivariant layer. So because if I translate the mug in the input, I would want my numerical features that I learn to translate as well. So we can define such layers through the group action on the input images and also on the intermediate features of the parameterized function. So this is a very important thing. The local pooling layer, we discussed it. This is a function that coarsens our geometric domain such that we are able to reduce the dimensionality of the numerical features. And through a series of compositions that are alternating, we can reduce that dimensionality enough such that at the very end, we can have an invariant global pooling layer. So this basically tells us that if you can think of this as having the mug and just forming all different translations possible, and then in the end, we're just gonna average all of these numerical representations such that the final function is invariant to where the mug is on the picture. So this is really the blueprint that we can use, and we can make explicit constructions to make this work. And it works better than if you just rely on labels that are given by human. It's much more efficient in terms of the performance that we can get. So now I want to transition on something else. And this is basically the second approach that I'm very interested in, is how to bake in invariances, not by constructing the function, but by guiding the optimization process. And the motivation for this is that the MUC, like the geometric property of this MUC is that it doesn't matter where it's translated. But there's another property that we care about. For example, we don't care about the color of the MUC. But this is something that's that doesn't correspond to any group action. So we need to find some ways to bake in that type of invariance into our model as well. And I will show you a problem that we've been working on with my current professor in physics to kind of like show you a nice test bed for this type of experiments. So in this current problem, what we do is we study nanophotonics. So we study materials that are whose intrinsic dimension is at nanoscale. And these materials, they are forming an infinite lattice. So the modeling of these materials is as if they are forming a lattice, and basically there's a unit cell. So there is some kind of structure in the unit cell, depending on the material. And this is repeated infinitely in both directions. And it turns out that there are certain, basically what we do with these materials is we shine light on them, and then we see how light interacts with the materials. And there are different physical properties of these interactions that we study. So the interesting thing here is that we have a lot of background knowledge. And that is, we have knowledge about what the symmetries of the physical properties are. So we know that if we act with the dihedral group on this unit cell, we're not going to change the physical properties. We also know that if we choose a different unit cell of the same lattice, then which basically corresponds to periodic boundary conditions, we're still not going to change the properties of the physics prediction. So if we're building a model to simulate, to predict the physical attributes from the input, these types of invariances are very useful. And it's not very clear how to construct an architecture for the function that satisfies those things. And that's why we basically resort to other methods to bake in that knowledge, and these methods are given by the following training objective. So the training objective is as follows: we take a collection of unlabeled examples. So we don't know what the physical properties of these examples are, but we can still extract useful information. So in particular, I can take two of these examples. This is example 1 and example 2. These are just two unit cells of the lattices that we care about. And because I know it has to be invariant to some transformations, I can actually construct those transformations myself. And then I can feed both of these transformations as inputs to my mathematical function, to my encoder. And the outputs of these transformations, I would require, I would have a training objective that brings them together. Because I would, and by requiring these outputs to be attracted, I'm gradually baking in the invariance property to that type of transformation. So there are other details that we can still take advantage of having different unit cells, because these are different unit cells. Even if we don't know what the properties of these unit cells are, we can still require the numerical features to be different from each other. So this works very well. It allows us to reduce the annotation that we require to solve these problems by an order of magnitude, and we're very excited to continue exploring this direction of research. Now, I want to finally conclude with another direction of research, and that is when we try to bake in not only invariances but also equivariances into the models. And what is the motivation for this study? So imagine that I want to classify a bird to predict that there is a bird in the picture. Then certain invariances would be useful. For example, I can do a mirror flip of the bird. I can blur the image as well. And I know this doesn't change the information on the picture. So I know I want my model to be invariant to these types of transformations. And this is what I showed you in a few slides ago. We can achieve that with this alignment objective that we have here. Basically, we want to align the numerical features that the model outputs. However, if there are some other transformations that we care about, for example, is it the same mug if I rotate it by 90 degrees? I guess we would say that yes, it is, right? So it's okay to conjecture that it may be good to rotate the bird, for example, by 90 degrees, and then say that I want the representation of a bird in an upright stance and a bird that's rotated by 90 degrees to be the same. I want numerical features of this input to be the same. However, the issue is that if you try to do this, if you have certain performance, then if you add this component, the performance drops noticeably. And this is not very surprising. It basically has to do with the fact that the way we collect our data is biased. In every image that we collect, we have a notion of an upright stance. Basically, it's not very common for people to take pictures that are rotated by 90 degrees and put them on the internet. So even though we know that it's probably the same object, that's not captured in our test set. And here comes the issue, is that we like the measure of success is very dependent on the type of test data that we collect. And the question is, okay, so it seems that rotation is not very useful to perform better on the test set, but can we actually go in the other direction and still learn some useful things about that bias? And here comes the idea that instead of aligning the different numerical features, we're going to enhance them. And I call this equivariance enhancing, because I want, if there's a bias in my data set, I want to be able to be very sensitive to that bias, because I want, if I rotate my image by 90 degrees, I want to be able to predict what type of transformation I have applied to the input. And this is exactly what we do with this simple method. We just take the bird and then we rotate it in with fourfold rotations, and then we predict what the rotation has been. And this motivation brought us to a framework that basically extends the way we build in features. We not only think about invariances, but also we think about equivariances. We try to, if we have some biases in the data, we try to make the parameterized function sensitive to those biases. And I was thinking of how we can capture this in a more formal way. And I've been building a formalism to explain how this equivariance is being captured exactly. So I'm going to try to go through this in the next few minutes and just roughly give the high-level intuition, because I don't think I would be able to go into the proofs exactly. But in the formalism, we start with the collection of all images, and then we want to have a group of transformations. So you can think of these as rotations by multiples of pi over 2. And then what we form is the collection of the orbits of this group of using all images in our data. And then what we have further is the numerical features that we get from this X prime. And the thing that we want to prove is we want to show that the encoder that we're training, the model that we're training, is equivariant with respect to this group of rotating by pi over 2, but fourfold rotations. And there are certain assumptions that we need to make in order to make this equivariance possible. We need to, first of all, define what group action means, and for that purpose, we need two properties, two assumptions. One of them is injectivity of our functions, and the other one is something that I call the bias property. And this means that if the bias means that if we take an element from our data, it's an upright thing because of the bias, and if we act with some element from the group, for example, if you rotate it by 90 degrees, the requirement is that this is not, g of x is not an element from our original set x. And this is definitely true for rotation by pi over 2, because our images are not rotated by 90 degrees. So if these two assumptions hold, then we can prove that we have a group action both on x prime and a well-defined group action on x prime, and and S, and at the end of it, we're gonna get this equivariance property. So just finally to conclude, the results are very promising. We show that if we can exploit that bias in the data sets, we can improve performance on standard computer vision tasks in a noticeable way. With this, I'm just going to conclude. So I try to bring all of the things that I'm working on right now, so it may have been a lot of information, but I think the key takeaways is that there is some interesting structure in deep learning problems, and I showed you two ways to how to bake in that structure into the models. One by constraining the parameterization, and the other one by using a special training objective. And there are many open problems. For example, it's not clear what the best approach is, because they all depend on the way we optimize the parameterized functions. Another question is how to actually improve these two methods separately. And then the final question is, are these the right tasks? Are these the right objectives that we set for ourselves so that we can learn useful numerical features? There might be some other interesting tasks. So if you have any thoughts or suggestions, or if you want to chat more about this, I'll be really happy to chat anytime. And I think with this, my time is up. So thank you very much for the attention.
Thank you. Any questions to the speaker, comments? Well, perhaps I would like to ask such a question. It is known that specialists in approximation theory of physical or chemical processes, when they try to approximate numerically a function which describes such a process, they know that purely mathematical, very nice approximation may be may lose information about the nature of the physical nature, for example. Can you relate this approach to such?
Okay. Yep. So the question is by focus. So my understanding of the question is whether by focusing too much on this baking in the invariance and the equivariance into the functions, whether we are losing something about the nature of the problem that can only be captured by looking at the labels. For example, by looking at the physical predictions. Are we losing from this type of constraint? And then I think the answer to this question is goes to my motivation. The answer is yes, we are, and I think it's something that I don't think there is a formal study of it yet, but soon to become, hopefully. Basically, if we try to constrain the search space, and that is if we try to make the mathematical approximation that is based on the invariance and equivariance properties or some other properties in the physical studies, then we get this desired property, but the parameterization becomes difficult to be optimized. Basically, it's hard to continue optimizing this parameterization to capture the other information about the physics problem at hand, and that we see empirically. Basically, if we try to make, for example, a model that is invariant to rotation, then we're basically not going to capture easily what else is on the picture. So we would know that the thing should be invariant to rotation, but we may not capture that this is a mug versus this is a case for glasses. So I think the answer lies in the way we optimize these functions. So in practice, these functions are general function approximators, but if we want to get to the optimal solution, it's a NP hard problem. So we need to think about how to what type of optimization we use to get there, and this is a field of exploration that is beyond my expertise, but it's very interesting, the interplay between the two things.
Thank you. Other questions? Well, I can't see. If there are no, let's thank again the speaker for this interesting talk. Yasumura. Excuse me, this is my mistake. He will speak about determining graded simple algebras by their graded polynomial identities. Please, Felipe, you have the floor.
Okay, thank you. Sorry. Okay, so thank you. So first of all, I would like to thank the organizers, especially Fleming, for the opportunity to give this talk today. So the question I want to address is the following. If we have two algebras satisfying the same set of polynomial identities, then is it true that both algebras are isomorphic? Well, the answer to this question is no. For instance, if you have an algebra, then it will satisfy the same set of polynomial identities as the two copies of itself. However, usually one has that both algebras are not isomorphic. Another family of counterexamples comes from unital commutative associative algebras over an infinite field. It is known that in this setting, all polynomial identities come from the commutator. So if you have the rational numbers, any field extension of the rationals, the polynomial ring over the rationals, then all these algebras will satisfy the same polynomial identities, but they will not be isomorphic. And one more interesting counterexamples is the quaternion algebras over the real numbers and the set of 2 by 2 matrices. They are not isomorphic since one is a division ring and the other is not. However, both are forms of the same algebra. It means that if we tensor with the complex numbers, then we will obtain isomorphic algebras, namely 2 by 2 matrices with complex entries. So, since R is infinite and C is a commutative ring, we obtain that both algebras will satisfy the same set of polynomial identities. So, it's natural to impose some restrictions to this expression. So the question will be the following. Given two algebras A and B, finite dimensional, simple, or prime over the same algebraically closed fields F satisfying the same polynomial identities, then is it true that both algebras are isomorphic? Well, in this context, we start to have some positive answers. For instance, if you assume that both algebras are associative, then this is very easy. It follows from Arbitrary-Levitsky theorem, given the minimal degree of matrix algebras and the structure of finite dimensional associative algebras over algebraically closed fields. For non-associative contexts, it becomes harder. So in 1983, we have a result by Koshkuley and Razmislov, proving that the result is true if we assume that both algebras are Lie algebras. Next, we have a result by Drensky and Racine in 1992, proving the same result for Jordan algebras. So it's remarkable that this paper, they showed explicitly showed a family of polynomial identities that can be used to distinguish the algebras, the simple algebras. And so on, we have another papers and works dealing with this question, and the strongest is due to Razmislov in 1994, where he proved in his book that the result is true for prime omega algebras. I will talk about this result very soon. Well, it is natural also to study this this question in the context of algebras with additional structure. So let G be any group. Let A and B be finite dimensional G-graded simple algebras over the same algebraically closed field. If they satisfy the same G-graded polynomial identities, then is it true that both algebras will be G-graded isomorphic? Well, if they satisfy the same graded polynomial identities, then they will satisfy the same ordinary polynomial identities. Then they will be isomorphic as ordinary algebras. However, it is not obvious how we can move to the to a G-graded isomorphism. Some papers were dedicated to study this question. The first one by Plummer and Delchev, where they study and obtain a partial result in the context of simple associative graded algebras. Note that even in the associative case, this question is not obvious at all. So other works were dedicated to this, and I will talk about the last one, which is a result by Baturi and myself, 2019. So I will state Razmislov theorem, and for this I will need some definitions. So we work with universal algebras, and universal algebra is a multilinear universal algebra in the following context. A will be a vector space over a field, and we consider set omega, which is a disjoint union of omega sub n, where n runs over the non-negative integers. And for each element omega sub n here, this will be operation on A, and this will be a linear operation in the nth tensor product of A to A. So A endowed with this structure will be called omega algebra. We will always assume that there is at least one operation that is to array or up. This means that we assume that this set is non-empty. It is well known that we can construct a free omega algebra, and it will be denoted by f sub omega x. So if you have a free omega algebra, then we can talk about polynomial identities of omega algebras, variety of omega algebras, with relatively free omega algebras, and so on. So a polynomial in the free omega algebra is called linear in the variable xi if it satisfies this relation. It means that if we fix n-1 elements of A, we can define a linear map from A to A given by substitution of xi by A. If we take all these linear maps together with the identity map, then this will be associative subalgebra inside the set of our F-linear endomorphisms of A. And this, we take the subalgebra generated by all these linear maps and the identity map, and this will be denoted by D of A. This is the multiplicative algebra of A. So obviously, A is a DA module, and we can define ideal, and ideal will be just a DA submodule of A. So the next construction, if we have two subsets of A, we can define their product as the subspace spanned by all elements of this form, where G is a polynomial which is linear in two variables. S1 lies in I1, S2 in I2, and A1 until AM are arbitrary elements of A. With this, we can define the following definitions. Omega algebra A is called simple if its square is non-zero and A admits only the trivial ideals. It means zero and the whole algebra. A is prime if whenever we have a product of ideals giving zero, then one of the ideals must be zero. And A is semi-prime if whenever we have an ideal with square zero, then this ideal must be zero. these definitions agrees with the classical definitions in the context of binary algebra, as an algebra with a single binary operation. Next, we need to construct the central closure of an omega algebra. So, as I said before, A is a DA module. So let P be an injective hub of the DA module A. Let E be the set of DA endomorphisms of P, and let Q of A be the image of A by elements of E. So by construction, Q of A is a EDA bimodule. Q of A is called the central closure of A, and it's possible to prove that this is an omega algebra, and A is a sub-omega algebra of it. And moreover, if A is semi-prime, then the action of E on this Q of A is commutative. It means that if you define C of A by the image of E inside the set of DA endomorphisms of Q of A, then this will be a commutative associative unital algebra, and it's called the Martindale centroid. It holds this equation, Q of A is C of A product with A, where the product is the natural action of C of A on A. Well, an important result to prove Erasmusov's theorem is the rank theorem. So to state this theorem, we need several definitions. So a polynomial, it will be called a Capelli polynomial of order K if it is alternating and multilinear in K variables. Let V be any vector subspace of A. Then we say that all Capelli identities of order K vanish on V if for any Capelli polynomial of order K, we have this equation equals 0, where we take a evaluation on all elements of V, V1 until Vk, and arbitrary elements of A in the remaining variables. The least integer K such that all Capelli identities over order K vanish on V is called the rank of V on A, and it's denoted by rank AV. So we get more one lemma. If A is a prime omega algebra, then the Martindale centroid will be always filled. And the rank theorem states a relation between the rank and the CA dimension of a CA subspace. So let V be a vector subspace of a prime algebra A. And if the rank of V is finite, then it holds this equation, the CA span of V. The CA dimension of this CA span is equal to the rank of V minus 1. So using this theorem, it is possible to prove the following consequences. So the first one is the following. If A2 is a prime algebra and A1 is a subalgebra of A2, and A2 is an L algebra where L is a unital commutative associative ring, and suppose further that A2 is equal to the product of L and A1. Then, in this case, we can find a relation between the central closure of both algebras. It means that there is an F-linear omega algebra isomorphism between these spaces. Another consequence is the following. If Q of A is equal to A, it means that A is named centrally closed. Then for any field extension of F, the algebra obtained by a scalar extension remains centrally closed. It holds this equation. Now, I want to construct generic algebra. This construction holds as in the case of associative binary algebras, and it can be made the following way. Let A be a finite dimensional F algebra, F omega algebra. and let A1, A2 until An be a F basis of A. Let consider the polynomial ring in infinitely many commutative variables. Let L be its field of fractions. Then we define this element Ri, which is the elements of the basis multiplied by variables. These elements lies inside the algebra A extended by the polynomial ring, which lies inside the algebra A with scalar extended by L. We let F tilde sub A be the F subalgebra generated by all these elements. So we are considering the F subalgebra inside this AL. And the lemma, which is not hard to prove it, is that this F tilde A is a relatively free algebra in this variety generated by A. So now, now it's also possible to prove that the L span of this subalgebra is the whole algebra. So from the first consequence of the rank theorem, we obtain this isomorphism between the central closure of AL and the central closure of the relatively free algebra. Another lemma is that if A is finite dimensional prime over an algebraically closed field, then A is centrally closed. So we have everything to prove the Razmислov theorem, which is the following. Let A and B be finite dimensional prime omega algebras over the semi-algebraically closed fields satisfying the same polynomial identities. Then both algebras are isomorphic. And the idea is the following. We consider the relatively free algebra. Since both algebras satisfy the same set of polynomial identities, the relatively free algebras are isomorphic. So using both consequences of the rank theorem, we obtain first this isomorphism, which I just stated, and A is finite dimensional prime, so A is centrally closed. The second consequence of the rank theorem states that after field extension, the algebra remains centrally closed. So we obtain this isomorphism. On the other hand, we can do the same thing with the algebra B, so we obtain an isomorphism between AL and BL. This is an F algebra isomorphism. We want to recover an F algebra isomorphism between A and B. So we can find an infinite degree field extension L tilde of L and an automorphism of the field such that we obtain a sigma semilinear isomorphism between these two algebras. It means that we find an additive bijective map Psi from AL tilde to BL tilde satisfying this relation. So we use Galois descent. More precisely, we use Hilbert Nostelizats to recover an F algebra isomorphism between A and B. So this is the idea to prove these results. Well, actually, Razmislov's results are stronger, and I will not state all the results. And here is one of them. Now we can go to solve our problem in the context of graded algebras. So the idea is very simple. Is the following: let A be a finite dimensional G graded algebra, and consider pi G the projections of A onto the homogeneous components of the gradient. Then define omega sub G as this union of elements, where here is a family of unary operations and a single binary operation. The unary operations on this G-graded algebra you act as projections, and the binary operation is the usual binary operation of A. And we have a translation between G-graded algebra and omega G algebra. And this translation works very well. So if A is graded prime, then it is equivalent of A being prime as omega G algebra. and a map between A and B is a G-graded homomorphism if and only if it is an omega G homomorphism. And moreover, we have a correspondence between the G-graded polynomial identities and the omega G polynomial identities. So using this idea, these translations and Erasmus's theorem, we obtain the following result, that if A and B are finite dimensional graded prime algebras over the semi-algebraically closed field satisfying the same set of G-graded polynomial identities, then both algebras are G-graded isomorphic. Well, we can also use the same ideas to generalize slightly the results. So first, we can consider G-graded omega algebras, where G is any semigroup. So it's natural how we define this object, and using the same ideas, we can prove that the result is true also in this context. Also, we can also consider H algebras, where H is a Hopf algebra. We can see the action of each element of H as a unary operation, and everything works well in this context as well. Well, there is also some open questions. For instance, if you have two superalgebras, then if they satisfy the same set of Z2 graded polynomial identities, then we know that they will be isomorphic as Z2 graded algebras. However, if is it true that they will be isomorphic if they satisfy the same set of superpolynomial identities? By a superpolynomial identities, we understand polynomial identity of the Grassmann envelope of the superalgebra. Well, we do not know the answer for this. And another question, which is natural, is the following. If you have two algebras where a set of polynomial identities of one is included in the set of polynomial identities of the other, is it true that we have inclusion of the algebras? Well, in general, this question is false. There are several counterexamples. There are some counterexamples, but we also have a positive result in this direction. If G is a billion, A and B are finite dimensional G-graded associative algebras over algebraically closed fields, then David in 2012 proved that this result is true. So this is what I wanted to talk today. Thank you for your attention.
Thank you. Any questions?
Yeah, can you go back to the last, hi Felipe, can you go back to the last, yeah, I must say that I spoke with Felipe many times. So about the last result of Ophir David, you say that for G non-abelian, this is false?
No, this is, I don't know.
Ah, you don't know. Okay.
Sorry.
And for super, what do you mean for super? I mean for simple superalgebras are Z2 graded.
Oh yes, but super polynomial identities in the sense of.
Okay, I understand.
Other questions? Well, if there are, at least I can't see. If there are no questions, let's thank again Felipe for his interesting talk.
Yes, it's an honor to participate in this conference. My name is Chavdar Lalov, and I'll be talking about Takayama's formula. This is joint work with Santiago Aranguri, Logan Bell, and Robin Truax, and it was done at the Stanford Undergraduate Research Program, and it was under the guidance of Slavana Prienko, who is a PhD student there. So before we begin, let us look at the plan for the talk. We will begin with some basic definitions, and we will introduce Takayama's formula. Then I'm going to talk about why Takayama's formula is important in its broader context. After that, we will talk about some new elementary proofs of Takayama's formula that we have developed, and then how they can be useful when studying variations of Takayama's formula. These are an area of modern research, specifically the symplectic Takayama formula, and we will finish with conclusion and future developments. So let us begin with a few basic definitions. A strict Gelfand-Zetlin pattern is a triangular array of non-negative integers that satisfy the start inequalities. The first start inequality basically says that each entry in the triangular array is in between the two entries above it. So in the first example, the 1 is between the 2 and the 0. Its value is between 2 and 0. The double start inequality means that each row is strictly decreasing. And here we can see a few examples. And now we're going to play with these patterns a little bit. We're going to take some combinatorial data. So we call an entry in the triangular array left-leaning if it equals the entry above it on the left. These are the squared entries in the examples below. Similarly, we say an entry is right-leaning if it equals the entry above it on the right. These are the circled entries in the examples below. And we call it generic if it's neither left nor right-leaning. These are the triangled entries in the examples below. And the combinatorial data we collect is the number of left-leaning, right-leaning, and generic entries. And what this allows us to do is to define a weight for each strict Gelfand-Zetlin pattern. And so the way, you don't have to remember this definition precisely. The weight is 1 plus t to the power of number of generic entries times t to the power of number of left-leaning entries times a product zi mi. And m1, the power of z1, is the sum of the entries on the first row minus the sum of the entries on the second row. m2, the power of z2, is just the sum of the entries on the second row minus the sum of the entries on the third row. So in the first example, with 2, 0, 1 triangle, we we have 1, which is a generic entry. So we have 1 plus t weight. And for m1, the power of z1 is 2 plus 0 minus 1, 1. And m2 is just 1 because there is no third row. And you can similarly compute the weight on the below triangle. Okay, let me pull that out. So now we are ready to state Takayama's formula. We'll see it again in the presentation. So what it says that if lambda is a partition, that is a weakly decreasing sequence of non-negative integers, and if rho equals n minus 1 and so up to 1, 0, then this very combinatorial sum on the left-hand side over all strict Gelfand-Zetlin patterns with fixed top row lambda plus rho, we are saying that the sum over all these weights equals this very algebraic product. We have a deformed well denominator times the Schur polynomial, which is the character of the polynomial irreducible representation of the general linear group. So it's hard to understand Takayama's formula this way. So let's look at an example. So let lambda be 1, 0, and rho equals 1, 0. Then lambda plus rho is 2, 0. We have 3 possible strict Gelfand-Zetlin patterns, and we can define the respective weight for each of them. Then what Takayama's formula says is that if we sum them over, we get this very nice factorization, where Z1 plus Z2 is just the Schur polynomial. But now the question is, okay, what's the point of all of this? We've kind of been playing around with some exotic looking combinatorial objects, and we have a combinatorial sum, which we say is equal to this other strange looking product. And it's hard to see like what's so nice about it. So there are 2 main reasons why we should care about Takayama's formula. The first one is that it's a very nice generalization of many well-known identities in algebraic combinatorics. For examples being Gelfand's parametrization, Jacobi's B-alternant formula, and also Stanley's formula on Hall-Little polynomials. All of these can be deduced from Takayama by simply specifying the parameter t. But there's a second, much more important reason why we should care about Takayama's formula. And till now in the presentation, we've basically been looking at the second and third box in this flowchart. The second box is the weird looking product, and the third box is the combinatorial sum with Gelfand-Zetlin patterns. However, the first box in this flowchart contains a function called the spherical Whittaker function, which has many important applications in number theory, representation theory, and geometry. And however, it would be nice, what many mathematicians have been working on is understanding this spherical Whittaker function. And it turns out that there's a direct connection with the so-called Kasselman-Shalaika expressions we've been looking at. But these products are still not very nice to work with. And so mathematicians have been trying to evaluate them in terms of combinatorics. So that's where this important connection of Takayama's formula comes in between the second and third box. So a little bit like the prime number theorem, Takayama's formula has brought a lot of attention to, and there have been a lot of different proofs of Takayama's formula. And here we'll look at, I will summarize and review a few of them. There is an inductive proof with symmetric functions by Bump. The main ingredients in his proofs are Pierre's formula and also branching rules for the Schur polynomial. There's also a combinatorial proof with determinant identities by Okada. And there the main ingredients are lattice path systems, the Lindstrom-Gessel-Vienot lemma in graph theory, and some complicated determinant identities that are similar to the Jacobi-Trudy identity, but are much more complicated. There's also another proof by Brubaker, Bump, and Friedberg, and maybe the most elegant proof of them all. It uses a bijection between strict Gelfand-Zetlin patterns and gamma-ice configurations, so a lattice model. And of course, the main tool is the Young-Baxter equation. However, there is one big drawback to all of these proofs, namely that they all use either heavy machinery or ad hoc techniques. And when trying to study Takayama, when trying to find and prove Takayama-like formulas for other groups, apart from the general linear group, these proofs are either hard or impossible to generalize. And so one of the main goals of our project was to find elementary proofs of Takayama's formula that can be used, that we can try to use to study Takayama-like expressions for other groups. And we have devised two such proofs, which both rely on the same principle, which is begin with that combinatorial sum with the weights, and then extract factors of the form zi plus tzj, and then specialize the parameter to actually prove Takayama's formula. Our new proofs avoid the major downsides of all three previous proofs. We have one combinatorial proof and one more algebraic one. So due to time constraints, we will only talk about the combinatorial proof. So our main new idea is to introduce a new combinatorial structure called a primed strict Gelfand-Zetlin pattern. The way we define it is to put a prime, we take a strict Gelfand-Zetlin pattern, and then we put a prime on all left-leaning terms. For example, in the example below, we have in the first example with the 2, 0, 2 triangle, we can take the 2 on the second row. We see that it's left-leaning, and so we mandatory must prime it. Then for each generic entry, we can split it into two entries, one with a prime and one without. As a result, for each strict Gelfand-Zetlin pattern, we get 2 to the power of number of generic entries primed strict Gelfand-Zetlin patterns. For example, we have 2 triangles with the entry 1 on the second row, because 1 is generic. The main advantage of working with primed patterns is that we can define a much more comfortable weight for each of them. Here it is just t to the power of number of primed entries times this product zi to the power of mi. And what we managed to prove is that we can, in order to prove Takayama's formula, it is actually enough to prove our new combinatorial Takayama formula. So we proved that these two formulas are equivalent. And the difference is that in the classical, we sum over strict Gelfand-Zetlin patterns that have a very complicated weight. And our advantage is that if we sum over primed strict Gelfand-Zetlin patterns, the weights are much nicer, as you can see. And now our goal becomes to actually prove the combinatorial Takayama formula. Here is a small example demonstrating that the formulas are indeed equivalent. So in the first column, so let lambda equal to 1, then lambda plus rho is 3, 1. And in the first column, you can see all possible strict Gelfand-Zetlin patterns. There are 3 of them and their respective weights. And in the third and fourth column, you can see the data for the primed strict Gelfand-Zetlin patterns. And you can see that the 3, 1, 2 triangle actually splits into 2 possible primed strict patterns. Nevertheless, the sum of the weights remains the same in both cases. They both have this very nice factorization. And below z1, z2 times z1 plus z2 is actually the Schur polynomial with lambda to 1. And essentially you're producing a completely different delta one equation. Our main idea is, in order to prove Takayama's formula, is to pair them. And we managed to pair them in such a way that the weight of each pair is divisible by z1 plus tz2. And if the weight of each pair is divisible by z1 plus tz2, then the whole combinatorial Takayama formula is divisible by this factor. Here we can see a simple example with top row 2, 0. And indeed, you can see that we can pair them so that the weight of each pair is divisible by z1 plus tz2. Our main achievement is that we managed to algorithmize this procedure. The algorithm works as follows. Look at the second row of a primed strict pattern and take the first entry from left to right, for which we can either remove a prime and decrease the entry by 1, or put a prime and increase the entry by 1. So in the first example, we look at the second row, we see the primed tree, and we notice that we can decrease it by 1 and remove a prime without creating an invalid pattern. In the second example, you cannot decrease the primed 2 because you will make a non-strict row, but what we notice that we can decrease the primed 1. What we managed to prove is that this algorithm is actually well defined, and moreover that it is an involution. It is its own inverse. So if you run the algorithm on the patterns on the right, you will get the patterns on the left. After we have this pairing and we have extracted this Z1 plus TZ2 factor, we basically use symmetric arguments to prove that Zi plus Tzj divides our combinatorial Takayama formula for all ij. And after we have extracted all the factors, there is actually a standard method, which we will not show, that finishes the proof. After you have all the factors, you divide, and then you can try to prove that what's left over is the Schur polynomial. Okay, but now again, why should we care about all of this? So we have a new elementary proof of Takayama's formula that doesn't use any heavy machinery. So why would we even be interested in this? And the main reason is that there is an even more general context. We can view the spherical Whittaker function. And the spherical Whittaker function can be considered with respect to an arbitrary reductive group. So not only the general linear group as we talked before. And similarly, there's a well-known and understood connection between spherical Whittaker functions and so-called special functions, particularly the Kasselman-Chalaika expression. But the connection between the second and third box is very poorly understood for a general reductive group. So if we have a symplectic group, there is a relatively good understanding, but even there's no understanding for the orthogonal group or any other reductive groups. So in 2012, Ivanov proved the Takayama formula for the symplectic group. Here you can see it. By using lattice models. It is an extremely complicated proof. It also needs a lot of computer computation, a lot of computer programming and computations. But analogous formulas for the orthogonal group or any other reductive groups are not known. They're not even conjectures, and let alone proofs. And so we basically tried to use our, let us look a little bit more in the symplectic group case. You can again define Gelfand-Zetlin patterns. And in this case, they're not triangular arrays. Their shape is a little bit different, as you can see. So here are a few examples. I don't plan on going through the definitions in detail, but again, you kind of have this in-betweenness condition as you go down, and again, rows are strictly decreasing. So our progress in this case has been only partial. We have managed to make some non-trivial results towards the direction of proving the symplectic Takayama formula. And our plan currently is to continue working on it and to try to find a proof that does not require lattice models. because lattice models is a very ad hoc techniques, and it's difficult to motivate why we need them in order to prove these very algebraic results. So the main question is, can we use our elementary model, our elementary methods from the general linear group and apply it to the symplectic group? And it turns out we can again define this new combinatorial structure called the primed symplectic pattern. And you again get this very nice weight. It's much easier to work with. And we can again prove that the classical Takayama formula is equivalent to a new combinatorial Takayama formula. So you have a sum over primed patterns. And now we want to prove that it actually equals this factorization. And so here it is again actually enough to extract the factors. We again focus on these factors: 1 plus t zi squared, 1 plus t zi zj inverse, and 1 plus t zi zj. So we want to prove that each of those divides the sum on the left. And we have already managed to extract one of the factors, specifically 1 plus tz1 squared. And after you have extracted this factor, again, all the factors 1 plus tzI squared for an arbitrary I, you immediately get those factors as well. And which we managed again to find the pairing algorithm, which extracts this factor. And the algorithm is fairly similar to the one we saw below for the general linear group case. However, the other two factors, the 1 plus tz1 z2 and 1 plus tz1 z2 inverse, are much harder to crack currently. We do have informal algorithms, at least that we conjecture should work, and that can actually pair all the patterns in order to extract these coefficients, but we are still far from a rigorous proof. And the main obstacle is that the pairing algorithms become much more complex and require changing multiple entries. As you can see here, we've changed 3 entries in order to make the pairing. So probably we can make it faster by just making it faster. And our main technique so far is to use a divide and conquer approach, basically pair some patterns, set them away, then pair some more patterns, set them away, and so on and so forth. For example, for the factor 1 plus tz1 z2, we have this lemma. I'm only presenting an intuitive version. We basically prove that we can pair almost all primed symplectic patterns so that the weight of each pair is divisible by 1 plus tz1 z2. And this can be achieved with a simple algorithm. And what the lemma says is that the patterns that are left that we still want to pair have a very tense and restricted structure. So maybe because we're left with so few patterns, we can actually pair them with more complicated algorithms. And so in order to summarize, the modern known proofs of Takayama's formula are very difficult to use when trying to prove Takayama formulas for other groups. For example, the orthogonal group, we don't even have a conjectured algorithm. And for the symplectic group, we only have a extremely complicated and ad hoc proof using lattice models. And this motivated us to try to study Takayama's formula through elementary methods solely, so that these elementary methods can be applied to any type of group. And our future directions include finishing a proof of the symplectic Takayama formula and trying to find Takayama formulas for the orthogonal group and other reductive groups. Professor Daniel Bump has also suggested, who is a professor at Stanford University, has also suggested that these primed patterns that we talked about, they may have a connection with crystal bases. and representation theory. So that's one direction that we will be studying actually with him during the fall. Also, Professor Boum suggested that there may be a new solvable lattice model hidden behind the structure of primed patterns again. So these primed patterns seem very interesting, and they may have, the reason they work may be that they have connection with some very rich theory in lattice models or crystal bases. I would like to thank Slava Neprienko, who was our mentor during the summer. Also Professor Boum for all of his advice. To Pavel, who was the organizer of the Stanford Research Program. Then I would like to thank Professor Drensky, who actually wrote me a recommendation so that I can participate in this summer research program. And also I would like to thank him for all of his help during my high school years when he was a research advisor for me. And finally, I would like to thank the Stanford Research Program and Stanford University. And here you can also see some of the main references that our group has used. Yes, thank you.
Okay, thank you. Any questions or comments?
In a symplectic case, you could say well-known and interesting things by setting t equal to 0, 1, and -1, like you do in the general linear case.
Yeah, that's a very good question. I haven't seen such formulas. Something interesting is that so there is this work by Hamel and King where they prove something very close to this, but it's very weird because they don't manage to. It's a very similar formula, but it doesn't look exactly like this. And the Hamel and King formula has some nice corollaries in terms of like expressions similar to the Jacobi-Trudy identity, but they're much more complicated. You have like matrices where you have complete symmetric polynomials, but with like a different number of variables and different degrees. So there's certainly some kind of very rich combinatorial and algebraic structure, but specifically for the symplectic case, I don't know if in this formula, if you plug 0, 1, or -1, I don't know of well-known identities. Yeah, thank you. I'll also look into it, but yeah, I'll also ask my advisors if they know something.
Other questions? I can't see. Well, if there are no further questions, let's thank again the speaker and I'm closing today's session.